max 3 classes?
Till school starts. There's no reason we can't keep going.
Right.
I just probably won't do any after school until this class is over. And we're going all the way to chapter 8. Sorry, what?
Even if this is on Monday?
Well, once school gets going, then this will either be on Tuesday or Wednesday. It will be on the day I'm teaching. I'm not teaching 2 days. I'm only going to teach 1 day.
Shoot, okay.
So, that's what will be when school starts. Last year it was a Tuesday, so it would most likely be Tuesday again. But it's possible that the schedule switches. So, we'll see. And all you guys will be in my classes anyways, right? You can go get some special permission to sit in on my calculus class and actually learn it this time.
Hey, we're getting out of the border store, of course.
Border store?
Yep.
That's, if you got border store, that's when you go start college.
Oh, is it?
Yeah. And that's a cush job, and at the same time, it's a job that guarantees you're not getting sent out of town. So you don't have to worry about starting a college class and being sent out of town and having to pay back your tuition and pay back your financial aid. Because you'd get it, I bet. Probably. Now, you're the last one, so maybe you don't. I don't know. Maybe you're going to have to do it like us Karen kids.
What'd you do?
Have to pay for it myself.
You never got financial aid?
Nope. Well,
Why?
technically I got financial aid, I never got Pell Grant. So
Right,
they
so
had
yeah,
student
same
loans available to me that were no interest till I got out of school. And so yeah, I had to take a student loan because I was on my mission when I started. But I also paid it back right afterwards. I only had the loan for like a year.
So should I go sign up for fall? I guess it's already passed, right?
You're probably too late for registration. I mean, you're definitely too late to apply for financial aid.
Mm-hmm.
But you should try for the spring, for sure.
Classes for the college start on like the 24th through the 21st or something of August.
Well, yeah, and technically, even I think after the first week goes, you can still get into classes and drop classes and stuff like that.
Right.
So yeah, you're probably not too late for registration, but for sure for financial aid, I bet you're too late for Pell Grant. I don't know how the loans, they vary, but anyways, let's get started. Let's start with going over the problem that we were doing last time. I just want to go over the whole problem. So you'll notice that the problem starts out giving us these 2 axioms, and then it gives us these 2 definitions, and then it just has prove a bunch of things. Now, the reason I want to stick with this problem so much, and the reason I want to make sure that we can all go through this problem is this is exactly what happens in mathematics all the time. Any field of mathematics, it starts out with a couple some axioms. You might throw some definitions along the way, and you start proving theorems.
My question in this specific example is, I don't understand, the predicate seems so vague. Because how are we able to, what did the I stand for? Again.
Well, remember that's an interpretation you're applying to it. Really, it doesn't matter what the Q stands for, it doesn't matter what the I stands for, it doesn't matter what the P stands for.
I understand that.
They said one valid interpretation, in other words, an interpretation you can apply to make your premises still true is greater than or equal for the Q, greater than for the P, and equals for the I.
So, okay, that's right.
So that is an interpretation that you can apply to it.
So, and you're saying in a typical math problem, they'll already give you the definitions, you won't need to search for those?
Well, you develop those definitions as you go along. Right, so in calculus, for example, we started out with our axioms on the real numbers. And one of the first definitions we made was, I can't remember how exactly it happened, but it was probably like defining what it means to be less than. And we had some ordering axioms, and we were able to define what it meant for one number to be less than another number. Or something we might have defined was what it means for a number to be negative. One of the definitions we came up with was a definition for the natural numbers. So then we just started creating definitions and using those definitions. And you start proving things about those things you defined. Very common thing to do. But yeah, we did the exact same thing. We started out with just, here's the axioms on the real numbers, and we went to work. Same exact thing. We start with the axioms right here, and we're going to go to work. We're going to create two definitions that seem useful to us, and we're going to prove some things. We're going to use those definitions. Notice you don't have to use these definitions. We can always keep everything in terms of Q's. We never need to introduce an I, and we never need to introduce a P. It just makes it easier to talk about.
Right.
They seem to capture some useful idea that we like, and we can keep talking about it. There's no reason in all mathematics that you ever have to use a definition. A definition is just giving you a shorthand way to say something that you already know how to say.
So we could say I in terms of Q real easily.
Yeah, it's just, anytime we have this idea, we can now just represent it that way.
Right.
That seems like an easier way, a useful way for us to represent it. And here might be a useful way to represent that.
Okay, those were written out a lot more obvious than I was looking at it before. Okay, that actually, yes.
Yeah, so if you want to imply an interpretation of greater than or equal and greater than, let's write these out with the symbols that we're comfortable with. So what are we saying? We're saying that we know that x is equal to y. That's logically equivalent to x is greater than or equal to y and y is greater than or equal to x. If you pick two numbers such that x is greater than or equal to y and y is greater than or equal to x, you pick two numbers that happen to be equal.
Mm-hmm.
Right?
Right.
So that's, if we use that interpretation, that's what this is saying, and then this one's saying that if x is greater than y, that's the same thing as, it is not the case that y is greater than or equal to x. Y is not greater than or equal to x means x is greater than y. And that's what this is saying.
So Q is greater than or equal.
Yeah, that's interpreting the Q is greater than or equal. That makes I equal, and that makes P greater than.
Right.
Good?
Yes.
Now that's just interpretation. We can do everything that we're going to do without actually making that interpretation.
Right.
And that might just help our intuition. Maybe that helps us think about the problem. But the fact of the matter is,
But
these Q's, I's, and P's really have nothing to do with these symbols. It's just our interpretation of it. There's hypothetically infinitely many ways that we can interpret that and have it valid and think about it. This one just happens to
what's
help our
stupid
intuition.
is our final line is in terms of Q, which is alright.
Well, it just depends on what we're trying to prove, right? So, in some simple math, they might say, prove that this number is even. They said even instead of divisible by 2. Ah, how dumb. Why didn't they say prove it's divisible by 2? Why did they say even?
Right.
Nothing wrong with it. Right? Okay, so we're just going to go through these A through H real quick, doing all these. And I have 3 written out here for the sake of trying to save time, and then to introduce some shorthands I'm going to start using. So the first one says, prove that for all x, x is indifferent to x.
Okay.
Right? That's what A is saying to prove. Saying using these premises and these definitions, we're going to do A. And remember that when he does just the x in parentheses, that means the for all x. So we're going to prove that for all x, x is indifferent to x. Or using our interpretation, for all x, x equals x. That's what we're going to prove. And we're going to show that that is a logical consequence of these axioms.
Then you universal simplifier, whatever you call that.
Yeah, so let's jump right out the door. So for all these proofs, you'll notice I'm just going to start with line 5. Because my 1, 2, 3, and 4 are always going to be the same. Just all the information we have. And in these proofs, I'm not necessarily going to use them all. Like in this one, I happen to only use 2 and 3. This one, I only use 3. This one, I only use 1 and 3. Make sense?
Yeah.
I'm just writing them all out so that we can use them every time in case we need them. Okay, so the first thing we do is we do a universal specification on what? On 2. Right?
Mm-hmm.
If we know that for any 2 numbers, x is greater than or equal to y, or y is greater than or equal to x, then we know it's true for x and x.
The same number.
Yeah. This is for any 2 numbers. So I can replace that with any variable I want, that with any variable I want. Making sure I replace all my x's with the same thing, and all my y's with the same thing. I did. I replaced all my x's with x's, and all my y's with x's. Does that make sense?
Mm-hmm.
that says for any two x's and y's you pick, for any two things out of the domain you pick, this is the case. Or if we're thinking about in terms of numbers, for any two numbers you pick, this is always the case. If it's true for any two numbers, it's true for these two numbers. They happen to be the same number. Who cares? Good? Okay. So, universal instantiation on, sorry, what does he call it? Universal specification. Universal specification on 2 gives us xqx or xqx, right? Okay. And then xqx or xqx tautologically implies xqx.
So it doesn't.
Yeah, it does. If I know A or A is true, I know A is true.
Okay, yeah. I know, but I just, when then you're going, you can just pick one. Which
You can. That's going to be on your table of.
You can just pick one if they're the same thing.
Yeah. So if we come to our little table of useful tautologies, one of them is. Where is it? Oh, P implies P or Q.
P or Q is the same thing as Q or Q, no.
P and Q implies P and Q.
Not that one. Oh well, maybe it's on there, maybe it's not. But it's obvious to our intuition that if you know P or P, if you know A or A is true, you know A is true.
Yes, that was obvious. I just was.
Okay.
You couldn't do that if there.
We can write a truth table real quick if we need to.
Okay,
True or true is true. True is true. False or false is false. False is false. Okay, there's our truth table. It works. Next, we know if A is true, A and A is true.
Yeah.
Right? Okay. And then, notice that we're kind of like stopping in our proof to use our definition. Right? So this was using axiom 2. This was still using axiom 2. This was still using axiom 2. Now we're not using axiom 2 on this line. We're just going straight up to number 3, and we're doing universal instantiation.
Yeah, that makes sense.
You good? So this is just 3 universally instantiated. If this is true for any 2 elements, it's true for the same element twice. Right?
Right.
So x indifferent to x means xqx and xqx. That's what it means. So now, these two tautologically imply this. You get with that?
Yeah.
If I know xqx and xqx, and I know xqx and xqx is logically equivalent to xix, then I know xix.
On our homework, do we have to go through all those steps? Or could we jump the gun?
Yeah, so that's what I was going to say. From here on out, I'm going to skip this step.
Okay, yeah.
I'm going to say this, along with axiom 3, tautologically implies this. And I'm not going to bother plugging this step in. Make sense? Good with that? Okay, so when I come down here and do this one, I'm not going to have this step. I'm just going to say I'm using that definition. I'm using the fact that xqx and xqx is logically equivalent to xix. And then we know xix, now we do universal generalization, and for all xix. And we're done. That's the first one. Any questions? Anything weird?
So this next one is X, I, Y.
So next one's a conditional proof. So this one just says prove that this is the case. X is always equal to X.
Let's go back to our thing.
This next one, sorry, what?
Let's go back to it.
Oh, the book.
I want to see how it's written out.
It's going to be written out as the last line of my proof every time. It's just going to be prove that for all X, for all Y, X indifferent to Y implies Y is indifferent to X.
Which makes sense.
Yeah, which makes sense. Or using our interpretation, prove basically for any 2 numbers that if X is equal to Y, then Y is equal to X. Make sense what we're trying to prove? Alright, so back to the beginning. Now notice that this one is a conditional proof, right?
Why?
Because it's an implication, it's a condition, it's conditional.
Alright.
So this one was just proving something about everything in there.
Right.
This one's, I think all the other ones are proving conditional statements.
So you start with X, I, Y.
So when you're proving an if-then statement, you assume the antecedent and show that implies the conclusion.
Yes.
Remember that we've done this a ton of times?
Yeah.
If I know that the premises, let's see, how was I going to do that? Something like that. If my premises and A implies B, then I can conclude that my premises implies and A implies B.
Yeah.
So I want to show my premises imply a conditional. That's the same as showing my premises and my antecedent imply my conclusion. These two are logically equivalent. We've written that truth table out a couple times.
I like it. It's one of the coolest ones.
So it makes sense why we're doing it. And you'll notice when it's all said and done, we don't use the premise that we introduced here. Alright. And we indent when we add a conditional premise, just as a helping us keep a corner happy. Okay, so introduces a conditional premise. X is indifferent to Y. Right? That's this part. Add that as a premise, that's now premise 5. And this line now depends on itself. Okay. So, if I know X is indifferent to Y, using the definition of indifferent, I know XQY and YQX. That's tautologically implied by this line and definition 3, so now we're using premises 3 and 5. Everyone good up to here? Alright. So, we know that A and B is the same thing as B and A. So, this line's tautologically implied by this line. Just switch the order. Good? Okay. And notice that that's the definition of Y is indifferent to X.
Right.
So X is indifferent to Y means this, change the order means this.
These are so petty.
So we show that this, if this is true, then this is true. So we showed that this conditional is true. And notice now we no longer depend on premise 5. Make sense why? Why don't we depend on premise 5 anymore?
Because you have your conditional premise. With your premises and your conditional premises, implying something means your premises imply the conditional premise and your something.
Dude, that is harder to follow than any sentence in this book. All right.
To write.
Anyways, so we showed this. We showed X is different to Y implies Y is different to X, and then we universally generalize. And we proved in the statement that we were trying to prove. Any questions on that proof? Good? Okay. Next one. What's the next one? It wants us to prove that if X is indifferent to Y and Y is indifferent to Z, then X is indifferent to Z. Or if X equals Y and Y equals Z, then X equals Z.
Right.
Make sense? Basically proving indifference is
Equal.
transitive.
I'm not good with those.
Yeah, you didn't get a good study of relations like James and Levi did. And like Leo will. Okay. Right? Oh, and Peter. I forgot, we have both of you. He says yeah. No hesitation there. Leah just smiles.
Peter doesn't know if he should do trig and
Yeah, I'm torn right now.
You're torn between what and what?
Trig, discrete, speech, chemistry.
no, not
No.
speech. Trig, discrete.
I want
Trig,
to take
discrete, anatomy,
I want to
chemistry.
take chemistry, human anatomy, trig, and discrete all
You
at
can't
once.
do that.
But I can't do that.
That's
Unless you
The
keep
first
it-
one you cross off that list is human anatomy, no question.
I love human
Told you.
I know, and I'm fascinated by chemistry more, but like human anatomy seems pretty cool. too.
Human
Oh.
anatomy is something you can always teach yourself.
Chemistry's on Wednesdays.
I'll admit that.
I
Human
forgot.
anatomy, you can teach yourself.
Chemistries are actually on Wednesdays.
Of course you'll admit that. It's a higher
Yeah,
level
that's-
science.
It's pretty easy.
Speech is good to in the morning or the afternoon.
Yeah.
You can pick which one.
So I can do all 4 of those.
You could do.
So you're going to take discrete math.
No.
You couldn't do anatomy. Anatomy's on Tuesday.
I hate for us to have to sit down and have a
It
conversation.
comes down to either
What?
choosing chemistry or choosing human anatomy,
Alright.
or not doing trig.
Oh, you heard Donnie's opinion. I like
My original
It's not an
plan was
opinion.
Trig, discrete.
Human anatomy.
It's
No,
dirty
it's
language.
trig. I wasn't doing the acronym.
That was my opinion.
College algebra.
Oh yeah,
It was trig, discrete, and then
You
speech
can
and chemistry.
teach yourself anatomy.
that's what I'm thinking.
Yes,
but I
for
don't
sure.
know yet.
Out of all those, the
Yeah.
easiest one to teach yourself is
Figure it all
anatomy.
out.
Yes.
The second easiest to teach yourself is
Awesome.
chemistry. The third easiest to teach yourself is trig. And the hardest to teach yourself is discrete math.
Alright. So if you want to know anatomy, you just go do a bunch of Google
You could
searches.
read the text. If you read the textbook and watched the crash course videos on YouTube, you would.
You'd probably learn
effectively-
more than any kid in that class, honestly.
I wouldn't
But
say
still,
that, but
that's
that's
what institution is.
Yeah, you'll have chemistry.
Yeah. I'll
Do
have
chemistry on Wednesday.
Chemistry and you'll be fine. Anyone who can do chemistry can do human anatomy. The reverse is true.
Savage.
Yeah, chemistry doesn't even get close.
It's like people that focus on application over theory. Everyone who can do the theory can do the application no problem.
Oh yeah.
Not everyone who can do the application can do the theory.
The
no problem.
application's the fun stuff.
You'll
to
go
see
to discrete
manifest.
math, your mind will be
If
blocked
you
out
can
here.
prove
You
limits,
go into
you can
trade
solve
math.
limits.
Yes.
If you can solve limits,
Doing
doesn't mean you
college
know
algebra
a thing
was-
about proving limits.
It was just like a breeze. Just read math.
Yeah?
College algebra. And that's what I'm thinking about teaching
Oh, you took-
next summer.
It'd be nice
Dude,
to have.
I don't want to miss another class, but you want this.
Wait, now how to prove?
Of course.
I would
Of course.
teach you college algebra. I wouldn't teach you how to solve a small section of algebra problems that happen to match up with real world applications.
Please teach me that.
Dude, I want that so bad.
Yeah, that's why I tried.
That or
That's
just do
algebra
something
classes.
like linear algebra.
Wait, so we get into like sine, or is that trig? I guess that's true.
That is trig. I don't know, I mean, the book I have, I don't know if it would somehow touch on that a little bit just for the sake of
Touch some for it.
introducing new maths to you.
Algebra
That's not its focus for sure.
college algebra, linear algebra, and abstract algebra. What are you leaning towards?
Ooh, I don't know if I could do. I'd have to think about an abstract algebra. That one would be a ton of fun too, though. Geez, I don't know. The one that's probably the most useful for my students would be college algebra. But I don't really want to teach something that isn't fun for me too, you know?
Yeah.
And then there's still other ideas
Calc
like
is fun, though,
topology. Anyone who's taking calc would love to do a topology course. Computation theory, that's another one I could do. That one has nothing to do with programming, just so you know. No point do you actually work on a computer. It's pure math.
Is it a prerequisite for
It's not a prereq for anything.
a CS degree? I'm saying, would you need to take a computation course?
So computation theory, some schools require it as a CS degree, some schools don't. So at Dixie it was known as by far the hardest class in the CS department.
Really?
What?
Yeah.
More than.
Now it's been
Topology.
changed. Topology is not a CS
Oh
department
yeah,
class.
that's not.
No.
Mathematics.
You do got a
Math department. Yeah, in the CS department, the only classes that were like math classes as opposed to programming classes that we took. Well, doesn't matter what they were, but there wasn't very many of them. And computation theory was one of them. And now it's got a new teacher and he's way easier and does it done. So new people going through get a worse experience, but the textbook is amazing. And I'd love to go through that with you guys. Mostly because I want to go through it again. Alright. Anyways. We were on this one, right?
Yeah.
Okay, so what are we proving? Oh yeah, indifference is transitive. That's what we're proving. Once again, this is a conditional proof. We're showing that this being true implies this is true. So, we start by assuming our antecedent as a conditional premise. It only depends on itself. Okay, now we're going to use the definition of indifference. X indifferent to y means xqy and yqx, right? That's using that definition. And then this is using this one's definition. So now we're using 3 and 5. With me?
Yeah.
Now all I did is reorder and add parentheses. We have xqy here. We have yqx here. We have yqz here, and we have zqy here.
Why is that?
Why did I group them like that?
Yeah.
They
For the
can
next line.
imply each other.
So now, notice what this one says. This one says q is transitive. If I have xqy and yqz, I have xqz. So now I have xqy and yqz. So these two together give me xqz, and these two together give me zqx. Right? Everyone see that?
Okay.
And that was tautologically implied by this line and using axiom 1, or premise 1. So from here to here, we're now using 1, 3, and 5. I don't want to go too fast. Everyone up to date?
Yes.
Let me look at a little bit. Okay, and then this is exactly the definition of xiz. xqz and zqx is exactly what xiz means. So we showed if these two are true, then this is true. And that was using premises 1, 3, and 5. Now we can get rid of 5 as a premise, come down here, and that finishes our conditional part of our proof. And then we just do universal generalization. Good? Okay, so that was the first 3. Now we're going to have to do these ones as we go.
Oh, you want to do all of them?
Yeah. We didn't even get to the one that you guys got stuck on last time.
Yeah, shit. Hey, would you pick the hardest one?
Is this
I
just
told
roll
you.
that way?
That one looks fun.
He did probably pick the hardest one. That one and then G and H use the same strategy. You have to do a proof by contradiction, basically. Alright, so we're on D now, right?
Yeah. X, P, Y.
One second. So we're doing for all X, for all Y, what?
X, P, Y implies Y, P, X.
That's not true.
Not
Not
Y,
Y,
yeah.
yeah.
Not Y, P, X.
I can't read it.
Okay, so let's do this one. Once again, it's a conditional proof, right? So we're going to introduce x, p, y as a conditional premise. I'm not going to bother writing out the stuff over here anymore because I think you guys can keep up, right?
But it's still doing our homework.
Maybe.
Yeah, do it on your homework. If you get confused, we can go back and plug it in.
Okay.
So that implies not Y, Q, X.
X, P, Y. What's the definition of x, p, y? That's the same thing as not y, q, x, right?
Well, why Q?
So look at our definition of p. X, p, y is not y, q, x.
Oh.
So just flip the order, switch the p to the q, and put a not sign in front. Make sense?
So then Y, P, X, you can say.
So if you know not y, p, x,
Then you
then you know
X, P, Y.
X, Q, Y.
y, oops,
X,
X,
Q,
Q,
Y.
Y.
From
and
what?
this is using our second one. We know that we have either xqy or yqx.
Right.
Since we don't have yqx, then we must have xqy.
Oh, true. Yeah.
You follow
I
that?
forgot how logic works.
Yeah.
Okay. Now I'm going to rewrite this a funny way. Not xqy.
Right?
Yeah.
You good with that?
Why do you do that?
You'll see.
Well, now I'm going to use this definition. Right? So I'm going to take this not part, the inner not, and replace it with this.
Oh.
So here's my outer not still, and then not xqy is the same
No,
thing as
y,
ypx.
Now it's
No, X, Q, Y.
No.
Why?
Oh,
Yeah.
sorry. Yeah.
Yeah.
Flip the order. And now we've got this implies this, and you know how to finish from there.
Yep.
Any questions about that? Do we need to finish out the proof? Do we need to plug
Did
stuff
you
in?
finish out the proof?
Finish out the proof?
Mm-hmm.
Okay, so we just did all this.
Mm-hmm.
So now what did we just show? We showed that xpy implies not ypx. And then we would universally generalize on that. So we say for all x, for all y, xpy implies not ypx. Is that good, or do we need to plug in more missing stuff?
That's
No, that feels good.
pretty good.
You feel like you can reproduce it yourself and fill in all the details correctly?
Easy peasy.
Mm-hmm.
Yeah? No? Something weird still? What did you like?
No, that's good.
It's good? Everyone good with that? I just don't want to take forever writing all the little pieces if you get the idea. Alright, so let's do the next one. Okay. What are we on?
E.
E? You want to just read it to me?
Leah do it because I can't see crap.
For all x, for all y,
For all z.
for all z,
xpy and ypz
xpy and ypz.
implies zpx.
XPZ.
xpz.
Oh, so this is one that got stuck on last time, right?
It's because the X's are written weird.
This is
Yeah,
E.
it's all italics.
Okay. So, once again, conditional proof, right? So we have x, p, y, and y, p, z as a conditional premise. Oops, forgot to end that. X, p, y, and y, p, z. Now we know what those mean. Those mean not y, q, x, and not z, q, y.
Yeah.
Right?
Yeah.
And now we know
X, Q, Y,
X,
x,
Q, Y,
q, y,
Y,
and
Z,
or.
y,
Or.
q,
Right.
z.
and.
No. I'm using,
Oh, yeah. Right.
I'm using
Number
2.
I'm using number 2.
If not this is true, then this one has to be true.
Yeah.
One of these two has to be true, since this one's false, this one's true.
Right.
One of these two has to be true, since this one's false, this one's true.
Right.
With me on that?
Mm-hmm.
Which is going to give me,
X.
I don't know if I need this.
X, Q, Z right now.
Yeah, we can do x, q, z.
Yeah, and then you double
So,
knot
I'm not sure if I'm going to need that,
that.
but...
You do. You double knot it now.
Well, no, I'm doing proof by contradiction. So now I'm going to introduce a not the conclusion as a premise and show that leads to contradiction.
Oh,
minute, wait.
that's not. That's
Maybe
not.
there's another way we can do it.
Why are you doing proof by contradiction?
Why am I doing a proof by contradiction? Because I'm. So this is a not Q. I mean. So there is no rules on how you should go about proving something. There's no written rule book. When should I do this way of proving versus this way of proving? Because there's no decidable way to prove something, right? That would be logically equivalent to solving the halting problem, which we showed last time is impossible. Right? You remember that proof?
Mm-hmm.
Yeah.
So there is no right way. That's why so many people love math. There isn't, oh, anytime you see this, here's what you do. I mean, there is that for very specific cases, but as a general rule, there's no list of things that you can do like that. So why try a proof by contradiction?
Just because you can?
Part of the reason is we're trying to prove something. Remember that this is really a not Q, right?
Mm-hmm.
This is the same thing. Where am I trying to get? I'm trying to get not Z, Q, X. And rather than having to try and come to a not something, I think it might be easier to assume it's true and then come up with a contradiction some other way.
Okay.
Might there be a way to do this without proof by contradiction? Yeah, there might. Who knows? There's no way to rule that out. But proof by contradiction is an option, and if it works, it works.
If you can prove that rule 2 applies to P as well as Q, so X, P, Y, or Y, P, X,
We know that's not the case.
because you can have and.
Well, just doing the interpretation of P as greater than, it is not the case that X is greater than Y or Y is greater than X. They can be equal.
Okay.
Alright. So, proof by contradiction. So I'm going to assume,
X, Q, Z is true.
I'm going to assume not XPZ,
Right.
my conclusion, right?
Mm-hmm.
So this is by way of contradiction. Notice now I'm double indented. Because once I'm done with my proof by contradiction, that's going to take me back to my conditional proof, and then when I finish my conditional proof, I'm going to finish the whole proof. Because this premise is something I can only use for this indentation. This premise is something I can only use for this indentation, and there might have been some larger proof that this is all a part of.
It's almost like a lemma.
It's almost
Except
like
the lemmas are bigger.
Well, it's exactly what it is a lemma.
It's just on a smaller scale, right?
Well, that's typically what you do for lemma. Lemma is, I don't want to do a proof within my proof, so I'm just going to do that on the side proof real quick
Yeah.
for my lemma. So I would do this part of the proof on the side real quick, and then come in and say, now from my lemma, and just go from there.
Mm-hmm.
So by way of contradiction, let's introduce this. Well, if we know this, what do we know? We know Z, Q, X. You good with that?
Yeah.
Mm-hmm.
Okay. So then we have ZQX and XQY. We know XQY from right here, right? That's what I was saying, I don't think I need step 8. 12, so if I know ZQX and XQY, what do I know?
ZQY.
ZQY. So then I know ZQY and what?
And what?
Not
And what?
GQY.
Or yeah. Thank you.
Even though I don't know how you know non-GQY.
Yeah, what does that mean?
It's not ZQY, it's right
Oh,
there.
it's
okay.
good.
That's what YPZ means.
I thought it was somewhere in your indent, but
So 14, therefore we conclude
XPZ.
if that can't be false, it has to be true.
oh,
So now we know
dude,
X,
I pretty love that guy.
So 15, then we know
Prove by contradiction.
XPY and YPZ implies XPZ, and then we could universally generalize that, and we're done. So yeah, we didn't need this line. And we didn't even need the YQZ. But
Yeah, you did.
no, where did I use YQZ?
Right there. Oh, ZQY, sorry, yeah.
Which makes sense, I didn't need to use all my information. If you think about it in terms of, we won't get into that. That would take some explanation and some drawing pictures. But, good?
Mm-hmm.
Any questions on the proof? Any weird parts? Any parts where it feels like I cheated?
Cool.
Yeah, I thought it was pretty cool.
Yeah, so really wasn't that hard of a proof. We just got in a weird spot. Maybe it's worth, and I think I understand why we got in a weird spot. We tried using all the information,
Yeah.
which is where we got in the weird spot. So maybe we'll do the interpretation of this and see why we didn't need all the information. So we were saying, if we know that x is less
was
than
this
y,
the one in class?
yeah. If we know that x is less than y and y is less than z, then we know x is less than z, right?
Yeah.
Now, there's a lot of information in y is less than z. All I need to know is whether or not y was less than or equal to z. I didn't need to know it was strictly less than z. Because if y is less than or equal to z and x is less than y, then I know that this is true.
Mm-hmm.
So this could have been less than or equal, and this could have been less than or equal. It didn't have to be less than.
Mm-hmm.
So we only need to use one of them as less than, which is why we ended up not needing this piece of information.
Right.
In other words, I could have proven the exact same thing if I would have known XPY and YQZ, then I would still be able to prove XPZ. And they did us an even stricter one. They put a P there instead of Q.
Right. Right.
Mm.
And similarly, if they would have given me an XQY and YPZ, I still could have concluded XPZ. If x is greater than or equal to y, and y is for sure bigger than z, then x is for sure bigger than z.
Right.
Right? Am I losing you in that?
Yeah.
Mm-hmm.
Yeah?
Yeah, but I don't think I need that because I understood the proof.
Well, the point was to give you intuition for why it was okay to let information go.
Oh, yeah, but you. It's okay to let.
It's okay to let information go, but why should you have you intuitively thought in your brain trying to prove it?
Everything.
I'm not using this information. Is that okay? Because most proofs you have exactly the information that you need by design to prove what you're trying to prove.
Exactly.
Okay. Anyways, so that was number
Letter E.
number E, or letter 5.
Shut up.
All right. Let's do the next one. Someone want to read to me what it says?
For all x, for all y, for all z.
No, for all z.
Oh wait. No, it's just for all x and for all y.
Okay.
X.
Z.
Okay, James, read for me.
What is
James should say it. There's no Z in that equation.
Z-I-Y.
How could you have a Z when we didn't
There's
introduce a Z?
literally X, I, Y is implied.
Thank you.
That's it.
X, I, Y, what?
Implies
Implies.
not parentheses X, P, Y, or Y, P, X, parentheses.
Oh, that was easy. You'll see it. This was real easy.
This is why.
So introduce x, I, y as a premise, right? That gives us x, q, y, and y, q, x.
Yeah.
Right?
This is going to prove itself. You just have to unravel the definitions, basically.
Yeah.
Yeah, and you could see how you would get it from this one, but let's go ahead and write these in terms of knots.
Not.
Are we proving this? X, I, y. Okay, I would guess. Never mind, doesn't matter. So now we're just going to put into knots, just for the fun of it. Not, x, q, y, and not, y, q, x. So now we get not y, p, x, and not x, p,
It's
y.
or.
No, you take
No,
out.
still and. I'm just plugging in definitions. Factor out the not, we get not y, p, x, or x, p, y, and maybe I need to flip the order. Not x, p, y, or y, p, x.
Boom.
And then you know how to finish it from there, right?
Yep.
Yeah.
Any questions on that? Do you see it all? It all makes sense?
Really,
So
they're
you
logically
can just
equivalent.
add knots, whatever you feel like.
This is logically equivalent to that.
It's like plus
Oh,
one
that's
minus
true.
one in a proof. You can just.
If it's not true, it's true.
We had a conversation about that.
God was using your false implications galore.
Mom's like, no.
You can say anything on a false implication.
You can't say anything about false implication.
It's just pissing off all the wives.
Alright, so that's that problem. We'll move on. Someone read it to me?
We on G now?
I don't know. We're on whatever one's after what we did.
For all X and for all Y and for all Z. Then X, X, I, Y, and Y, P, Z implies X, P, Z.
I'm not sure if we're going to need to do a proof by contradiction for this one too. Let's start it and we'll just see what happens. So let's see. We start out with our conditional premise is x, I, y, and y, p, z, or x, p, z?
Y,
Y, P,
Y, P, Z. Okay, so what do we have? We have x, q, y, and
Y, Q, X.
y, q,
All them right.
x, and not z, q.
Why?
Y.
G, Q, Y.
Oh, that was right. For some reason I thought I wrote an x. Okay. Let's see what we're trying to get.
Not Z, Q, X.
We're trying to get not z, q, x. We're trying to get a not z, q, x. So yeah, I'm going to do a proof by contradiction on this one again and assume this so I can have that and see if I can build a contradiction with that. Okay?
So you're going to assume Z, Q, X?
Yeah, I'm going to assume not x, p, z and then write that same thing. So we have not x, p, z. Here's my by way of contradiction. So that gives us z, q, x, right?
Yeah.
And let's see, I want to create a zqy, so I have a not zqy here. So I'm going to use this to create a zqy. What do I need? I need a xqy, and then we'll have it. Oh yeah, so zqy, then I know zqx and xqy from right here.
Right.
Okay, I have a question.
Go ahead.
In this contradiction and the last contradiction, it's like, explain to me how it works, because you're assuming you're assuming the contrary doesn't work, right? Oh, sure, you're assuming the contrary does work.
And then you prove that it doesn't.
The intuition is prove it's impossible for this statement to be false. Therefore, it's true.
Yeah, he's making so if
Okay,
they
yeah.
were
I'm going to
false,
say, is it
not
false? That leads to an impossible worldview. Therefore, it's true. Or,
Our actions
here's
are off.
the law of absurdity. We're saying if you have P implies Q and not Q, that's logically equivalent to not P, not your premise. So, sorry, I said that weird. If your premise implies Q and not Q, a contradiction, that gives you not P.
Yes.
Anytime the left is true, the right is true.
Yeah.
That's another way to do it. Anyways, so now you know what we're going to do. We're going to use the fact that Q is transitive, and we get our Z, Q, Y. So now we have Z, Q, Y, and not Z, Q, Y. That's contradiction. Therefore, we know X, P, Z. And then you know how to finish out the proof from there.
Yeah. So much fun.
Easy peasy?
How did I come up with
What?
I'm confused to where you got your
Exactly.
X, Q,
Makes so
Y.
much sense
Yes,
here.
that one. Z, Q, X.
How did, oh,
X, Q, Y.
let me fix that. That's an X, Q, Y. So you're saying, how did I go from just Z, Q, Y to Z, Q, Y and X, Q, Y?
I'm wondering where you got the X, Q, Y from.
In and statements, they're all true.
What is line 6 saying? It's saying that I know this is true, and this is true, and this is false. So since I know that this is true, I still know that it's true.
So
Well,
it's
you know
or
that it's
the
true
whole
that
new
it's
case.
false.
Can you
I-
or three things?
Yeah?
Yeah, you can do it to any number of things.
Can you add 3 things?
Yeah.
And you can order.
So you can or like 1 of 10 are true.
You can or 1 of 10 are true.
You can
Well,
or
a set of 10
10
things,
things.
one of them is true, the rest are false, and it's still a true statement.
Yes.
I've never seen more than 2 ors that we've dealt with so far. That's
You need to see bigger boats. Got tons.
so stupid.
Alright. I think they're good there. Oh, sorry, James. Did we clear up everything for you? Well, are you good with this line now?
It's just weird to me that you just pulled it down, but I guess it's true, so it doesn't make any difference.
Well, just remember, we can use statements that we already showed are true. We already know that this is true. So we're just saying it's true again. It's like if I gave you the statement, let's say you know Donnie's in the house and the lights are on. And then you try to use the fact that the lights are on later on. I'm like, whoa, 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 you knew Donnie was in the house and the lights are on. You can't just go around saying the lights are on. Yeah, you can't. So, any other weird parts?
Nah.
Nah? Alright. Good? Next one? Someone get ready to read it to me?
It's not on there.
You gotta change your thing.
Oh. Sorry.
The last one?
I don't know. The one after the one we just did.
Yeah, well, okay, for all x, for all y, for all z. And x, I, y, and z, p, x implies z, p, y.
Is this the last one, Leo, or
That's the last one.
Okay. This one looks very similar to exactly how the last one was, so I'm going to use the exact same strategy and see if we get held up anywhere.
They just switched
Alright.
these.
So we know x, I, y, and
Z, p,
zpx, and zpx. So what do we know? We know x, q, y, and y, q, x, and not x, q, z. Now obviously I'm going to try and do a proof by contradiction where I construct an x, q, z. Take the not of this, so by way of contradiction, what are we going to assume?
not z, p, y.
Not z, p, y,
It's the same thing
or
as Z, Q, Y.
same thing as y, q, z. Flip the order.
Yeah, my bad.
Remember?
That's
Y,
right.
q, z,
Alright, now we have YQZ. We're trying to create an XQZ, so we need an XQY. There it is. So then we know XQY and YQZ. So now we know XQZ. So now we know XQZ and not XQZ. Contradiction. So then we know, what did we assume the not of? ZPY, and then
There.
you got it from there?
Yep.
What? So on, so forth, and so in the other ways too.
No,
He's a good farmer. He keeps going.
in all the ways that.
Yeah, gotta get the whole field. Okay. Good?
Back.
Did you have a question about something? And you're looking at me like you do with a weird grin on your face. Alright.
It's called the guilty grin.
The guilty grin.
It's called the GG.
Meaning that you have a question but don't want to answer or ask. That's what the guilty grin is.
The guilty grin. When you have a question you don't want to ask. I don't know why you'd have a question you don't want to ask.
A confused grin, honestly. Or confused something.
It's just called the GG.
Anyways, let's do the next problem too. So this one has these as premises, or as axioms, and then we're going to prove some things with these. Again, why do I want to do this? I want to just give you a set of axioms and show you how to prove theorems. That's what all math is.
This is.
So now we're going to go into a different field of math. We just finished geometry, now we're ready for algebra, right?
I'm missing your point.
We're jumping from one field of math to another.
Oh, because
We were using these set of axioms, now we're using a different set of axioms, we're going to look at their logical implications. I'll just-
plus and minus signs. False.
So maybe make a note, because I read how he sets up this problem.
What are the little?
So these are just symbols that he's using. So the plus is not addition,
So
it's just
like a
an
predicate.
operation symbol.
It's like a predicate, basically.
Yes, except for in this case it's going to be an operation symbol. Just like in discrete math we would use like I think we just
A
used a
star.
circle or a star for an arbitrary operation.
Uh-huh.
So he's using plus just as an operation.
We haven't
It takes two things together and it spits something out.
we haven't defined operation.
An operation takes two elements in your domain and spits something out.
It's a function.
It's not a function. You need a table to do an operation.
Table. Where is the table?
Well, that's how you represent it. So if I have a representation,
yeah, that's right.
okay, let's look at an operation that we know. We'll think about Boolean algebra and we'll think about the OR operation. The OR operation, how's it defined? So it can have a true and a false on one side and a true and a false on the other side. True, true gives you true, true, false gives you true, true, false gives you true, false, false gives you false. And you've had your operation table 4 times tables, and you had 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and you filled out your table with all the products of them.
Mm-hmm.
Operation, a binary operation, which is what we're talking about here, takes 2 and outputs 1.
Right.
Okay? So, we've got plus, some arbitrary binary operation. We've got C, some, I guess you could think about that as a function if you want, or a predicate.
My question is, why have we just been working with predicates and then all of a sudden he throws in an operation? And do we treat
It's a
it the same
predicate,
way?
isn't it?
So-
What's the difference in the way you treat predicates versus operations?
So, remember that operations on terms are just another way of writing a term. 1 plus 2 is just another way of writing the term 3.
Right.
Especially when the operation, all the ones that we use in this class, they're going to be closed, meaning it's going to spit out something that's also in your domain. So addition is closed under the real numbers.
Yeah.
You add 2 real numbers together, you get out a real number. Let's think about something that's not closed. Think about the integer z. So z is shorthand for the set of all integers. Do we all know what integers are? You know what integers are? Wow.
You need a prayer, press 1,
This chick
press 1.
keeps calling me and I don't know who she is.
Alright, anyways, so think about the integers. And let's think about the operation divides. Right? So if I were to look at 2 divided by 3, what's the answer?
2 over 3.
It's 2/3, which is not an integer.
Right.
So this is an operation in the integers. It takes 2 integers and it spits something out, but it's not closed. In other words, the things it spits out is not an integer.
Did we decided that modular arithmetic is closed, right?
No. So when you
Oh,
did
no, just
modular
addition,
division
modular.
in modular arithmetic, you needed them to be relatively prime to what you were modding by.
But modular addition was closed.
Relatively.
Yep. All of them were except for division.
Division.
Yep. Relatively prime, meaning their greatest common factor is 1.
And that's when we did the equation.
So 4 and 5 are relatively prime. What's their greatest common factor? 1.
Right, right.
Yeah.
Yep. Math checks out. Anyways, so you don't get to assume that you know anything about this plus. You don't get to assume you know anything about this predicate C, and you don't get to assume you know anything about this prime. I don't know what it is. I'm going to do it as a prime.
Just math.
That's just x prime.
That's what I'm going to call it. That's how I'm going to write it. I don't know what that symbol's supposed to be. It's just like a bar up there. It's not even a 1.
Does
Just
that
a
mean
line?
it's
It's
not?
just a line.
That sure is interesting. It's like an upside down.
I'm shocked their typewriter.
If
could
they're
put that
doing
in.
it like that, then does that mean it's not connected to the for all x? Or is it?
The for all.
Yeah. The x at the beginning. Because it has that.
They have that one
prime.
Oh no, it's just the way, think about it like to the power of 1, like an exponent.
Okay.
So it's a unary operation. Well, that's not technically true. Think about it as an inverse symbol. There we go.
Like to the power of negative 1.
To the power of negative 1 is an inverse symbol, right? What's
Yeah.
2 to the negative 1?
Yeah.
It's 1/2.
Yeah.
Right.
So think about it as a symbol kind of like that. It takes something and it does something to it that spits something out. That's somehow related.
Well, oh, it printed.
Okay.
It's an
So it's
operation.
actually doing something to it.
Yeah, it's an operation. It's a
Okay.
unary operation. So we have plus a binary operation, what I may call prime a unary operation, and a predicate C.
Prime isn't an operation, is it?
It's a.
It is in,
It's a representation of a different number.
it's often used in calculus to mean the derivative with respect to time.
Uh,
And in that sense, it's thought of that way. I mean, it can be whatever you want to be. And then when he uses logic in here, it's logic just like we know it. So the and is and in logic, and the not is not, where he uses a negative sign for not. But so the C, the tick, and the plus are not anything that you already know.
mhm.
They're just arbitrary things they spent here. Well, they do capture something, but what they capture doesn't matter right now. Good? So now we have our 5 axioms, and then when we scroll down, he's going to have a bunch of theorems for us to prove.
Go right them out so I
Five
can actually see
axioms.
them.
Huh?
5 axioms.
5 axioms, just like
And we're only gonna use number 1.
Just like
Don't
geometry,
translate 13 or
almost.
14.
you just have to add 5 more. Euclid, talk about,
Didn't Euclid only have 5?
he had 5 postulates and 5 axioms, and
Oh.
he used different
Aren't
names for them, even though
postulates
they're the same.
basically the same thing.
Well, he didn't have our modern notion of mathematics. He tried to do things that turns out they don't really work. Because, so we understand that when we're proving things in mathematics, we're proving that they're universally true. That they're in no way specific to this universe. You get rid of this universe,
And they're still true.
and all mathematical theorems are still true. They're no way dependent on the laws of physics. Euclid was trying to describe the world. He was trying to do physics. And he was trying to capture laws that you could always use in physics. So he wasn't really doing the exact same thing that we're doing, and he didn't understand mathematics quite the way that we did.
So
Although
what's the
what he
difference
did
in
is
the way-
absolutely amazing.
What's the difference in the way he uses axioms versus postulates?
Axioms are what he's using to capture what they knew as numeric relations, and postulates are capturing geometric
So based
assumptions.
okay.
So one of his axioms is equals added to equals are equal. One of his postulates are given 2 points on a line, there's a line segment that connects those.
Right.
And what does he mean by that? He means like there is in reality a line segment that exists between those 2 points. So he was thinking very much about the universe that we live in, and it took a long time for people to make the leap that
it doesn't actually apply to the real world, it's just an idea.
well, it does apply to the real
I mean,
world.
but it doesn't have to.
Yeah, that leap that there could be geometries that aren't this geometry. That took, it wasn't until Gauss came along that that was happening. So you're talking about almost 2,000 years where people are
Questioning.
still confused by this, because one of the biggest questions in mathematics was proving what it's called Euclid's fifth, but his parallel postulate. His parallel postulate, it's not the verbiage that he used, but a logically equivalent notion of it is, if I have a line and a point not on a line, then there's one and only one line I can draw through that point such that these two lines don't intersect.
Right.
And so people
That's
thought,
that's not like a theorem or anything.
yeah, that's a postulate. And so people thought exactly like you did, like, that seems like something we should be able to prove. And so they tried forever to prove from his postulates and axioms that this is true.
And they couldn't do it.
And they couldn't do it because the big conclusion was, while this happens to be the case on relatively small scales in our universe, it doesn't universally have to be the case.
What do you buy?
Because if you don't, so for example, if I accept that there is only one line that goes to that point, okay, now we're in something called Euclidean geometry. If I say there is no line I can draw through that point, now we're in something called elliptical geometry. If I say actually there's infinitely many lines I can draw to that point such that these two things never intersect, then we're in what's called hyperbolic
So
geometry.
what are the applications of those?
Huh?
Are there any applications of those geometries?
Oh, absolutely.
Where
So,
do they apply?
elliptical geometry applies when you're talking about geometry on the surface of the Earth. Hyperbolic geometry, one of the major applications of it is Einstein's special theory of relativity. I mean, so what often happens is,
That's right, we talked about
you
this.
need to remember that, okay, let's think about what,
Well, I remember
let's go from the top
We
down.
were doing that proof, and you had a triangle, and we couldn't use the Pythagorean theorem because you're like, this is not a Euclidean space.
Oh, when I was giving the relativity lecture.
Yeah.
Yeah, and we showed that our notion of Pythagorean theorem didn't follow there, but yeah, so Einstein very much relied on the fact that other mathematics have been done. It's like, well, let me just say it this way. So, you understand the notion of a high-level science intuitively, right? What's a high-level science?
It's a specific field.
No.
Okay, I don't know what you're saying.
A high level science like
Okay.
a social science or like physics?
Yeah, like a social science. No, physics is a fundamental science. So, build our pyramid
Yeah,
that we
your
always
pyramid.
build. So at the bottom of this pyramid we have math. And we could even put under this if we want logic. And then above math we have physics. And above physics we have something like chemistry. And above chemistry we have something like biology.
You get into the unknown of chemistry.
And above biology we might have something like human anatomy.
anatomy. And then psychology.
Well, we've gone far enough to make a point. So, all of math presupposes logic. All of physics presupposes math. All of chemistry presupposes physics. All of biology presupposes chemistry. All of human anatomy presupposes biology. Right?
Yes.
So that's what we mean by a high-level science in a way. This is the same concept that this abstraction is trying to capture is exactly what we mean by a high level versus a low level. Physics and chemistry, these are low level, human anatomy, biology, and then social sciences would be something even higher than that. Would be even higher on the scale.
Gender studies.
Gender studies is not.
Okay.
That's not a field of knowledge. That's a bunch of nonsense. Anyways, this is only building up science. This isn't building up something like history or philosophy. So, anyways,
Isn't history considered a social science?
isn't history considered a social science? It shouldn't be.
I know, but isn't it in reality?
Well, I don't care how someone chooses to classify things. If they're doing that, then they don't have, whoever is willing to do that, then if you were to ask them to give a good definition of science, what exactly do they mean with science?
It's different than the rest.
Then it's either going to be a different definition than what people use, or they're going to have some equivocal notion in their head, and they're not going to be able to give you an exact definition of science that works for everything. So maybe start out with logic and math is what we've pretty much been doing in this class.
Mm-hmm.
There's only one type of reasoning you're allowed to use in logic and math: deductive reasoning. That's it.
What about?
You can only look at the logical implications of assumptions. That's it. We never assert this thing is true. We assert if this is true, then something else is true. We assert that the implication is true. So we never say that x equals 2 is universally true. We say if x plus 1 equals 3, then x equals 2 is universally true. We don't say axioms are true. We say if axioms are true, then every single theorem that follows from those axioms are also true.
Right.
That's what we say.
Just one big implication.
We say the fact that the axioms imply the theorems. That's what's universally true. Tautological implication. Impossible for it to be false.
Logic.
So that's what we talk about when we're talking about math and logic. That's all we're interested in. Things that are universally true. They're in no way dependent on this universe. Completely change the laws of this universe. Math and logic, nothing changed. Take the universe out of existence. Math and logic, still as true as they ever were. Right?
Right.
And all you use is deductive reasoning. Now, once you get to the field of science, you're able to introduce something called inductive reasoning. And we know what inductive reasoning is. Hopefully we remember. But we'll remind you.
Over and over and over again, then you can make.
It's when you create generalizations.
Yeah.
It's you've seen the phenomena. Every time you watch a particular phenomena, then you make a generalization about it. That's how laws of nature come into existence. We call it a law by inductively reasoning on a phenomena happening over and over and over again. So at one point we had what we call the law of gravity, because we witness gravitational things happening over and over and over again. Right? I guess none of you have taken physics, so.
We all have a rudimentary understanding of that.
Right.
I took calculus, so I got some application from.
But one of the laws we might use is that relatively close to the surface of the Earth, gravity accelerates downwards at 9.81 meters per second squared. That's something that every physics student would get introduced with right out the door, something they'd be very comfortable with. Anyways, so we use inductive reasoning, but we don't just inductively reason on anything we want. You have to inductively reason on observable phenomena. It has to be inductive reasoning on what your senses communicate to you is happening. And it has to be on observable phenomena, meaning you have to be observing an object, something that you're seeing exists in reality independent of you, something that is public, a public phenomena, meaning another observer can witness it. So some physical phenomena happens, you observe it with your senses, some other observer can observe it with their senses. It has to be that kind of phenomenon. So you call it an observable fact, is the terminology that would be used. So it's an observable fact that when I dropped this marker, it fell to the floor. That's an observable fact. It is not an observable fact that I feel sad right now. Maybe it's the case, maybe it's not. There's no way for you to know that. Science isn't interested in that question. Science can't answer that question. All it can answer are questions about observable facts. Only things that can be communicated to you through your senses. So that's the foundation of science, is we start with just observable facts. We inductively reason on those observable facts to create laws, and we look at the logical implication of those laws. And we create mathematical models that do that. So we go and we look around our universe and we say, the best that we can measure, it looks like Euclid's postulates for geometry are satisfied.
Right.
Therefore, we'll assume that those are true for this universe, and then we use all of geometry from there on out. That's how we pick a particular mathematical model. So all geometry has its 5 postulates. We'll ignore axioms for a second, doesn't matter. So what do? We look around the world around us, and we say, yep, it looks like this, it looks like this, it looks like this, it looks like this, it looks like this every time I observe it. Therefore, I can now assume these things, and what do I get to use? I get to use all the theorems that these things imply from here on out. And one of those things that are implied all the way down here is a Pythagorean theorem. Every time we come across a right triangle in this universe, we don't remeasure to see does the Pythagorean theorem still hold in this case over here?
Right.
No, we're not worried about that anymore. From there on out, we assume it holds. Now, we could check the mathematical model. We could look at some of the theorems, see some of the predictions they make, and check the predictions. That's how you check if a model is good or bad. You say, I think this model works. It makes predictions. Then you can go and check the predictions. How can you check the predictions? It has to be observable phenomena. It has to be an observable fact that you saw something that you saw, or felt something that you felt, or whatever your senses were communicated with, and that someone else's senses could be communicated with, right? So that is what science is founded in. You take inductive reasoning on observable facts to create assumptions that you can apply mathematical models to that make predictions with observable facts, that you can check with observable facts. That's what science is doing. You can't do that with history. Science is all about creating generalizations. History is about recreating specific situations. It uses the counterpart to inductive reasoning. Inductive reasoning uses a bunch of observed specific phenomena to create a generalization. Abductive reasoning uses a bunch of your generalizations that you create to reconstruct a specific phenomenon. Right? What goes on in a courtroom is not science. What goes on in a courtroom is more like history. You're trying to reconstruct a specific scenario, a specific event.
The blood and fingerprints, right?
Yeah, and you can use science for history the same way that you can use math and logic for science. You can also use math for history, and you can also use logic for history, obviously.
Yeah.
Yeah, but you can't do the inverse. You can't historically prove Newton's theory of gravity.
Right.
You can't scientifically prove the Pythagorean theorem. You go measure infinite triangles in this universe and see that the Pythagorean theorem is true, and you still didn't prove it, not by a mile. You didn't come close to proving it. We all understand why infinite examples isn't a good proof when we talk about math, right? Because I can prove to you every number is even. Check it out. 2. Check it out. 4. How many numbers do you want me to give you? I can give you an infinite number. Therefore, every number is even, right?
No.
Just because all the ones you happen to check it worked for does not come close to proving something true.
Right.
Right? So even infinite examples, no, that's not proof. I don't remember why I got off on that tangent.
The question originally was, do you know what a higher level science?
Yeah,
Before that,
but
we were
I was
talking
asking that
about
question
axiom
to
versus postulate.
push something else forward. And I
Oh,
can't remember
axiom
what.
versus a postulate, yeah.
And before that was a connection. We had 5 axioms here. That's also
Okay, and then my question before that was, will you write them on the board so we can actually see them?
Yeah, I will write out the axioms. Okay, I'll write them out, but someone else again read them to me.
Okay, for all x and for all y, then you have bracket, and then you have c parenthesis x plus y parenthesis implies c parenthesis y plus x parenthesis bracket.
Oops. Parentheses.
For all x and for all y, then you have bracket c parenthesis x parenthesis implies c parenthesis x plus y parenthesis bracket. Okay, then 3. For all x, you have bracket c and parenthesis x, and then you have your prime thing, and then the parenthesis implies not c parenthesis x parenthesis bracket. Okay, and then for all x, you have bracket not c, and then parenthesis parenthesis x prime parenthesis implies c parenthesis x and then bracket. And then 5 is for all x and for all y. Yeah, bracket c parenthesis x plus y parenthesis and c parenthesis x prime parenthesis implies c parenthesis y.
Okay. Those are our 5 axioms. We ready to go, Jake?
What's the second one saying? I'm kind of missing that.
For all x and for all y, c of x implies c of x plus y.
What does that mean?
It means that for any two elements you pick in the domain, if c is true for x, then c is true for x plus y.
That way of writing that term.
What's plus in this case?
So it's basically saying it's closed in a way. It's kind of like saying that. It's true for this, then it's true for this and this.
Well, it's kind of like well, not and, it's more like how or works, right? If you know that something's true for one term, you know it's true for a term or another term. You can or on another term if you want.
Okay.
Or if it's false for one term, you think about it as and. So if this is saying it's false, then this can be saying it's false for that and that.
Wouldn't they just write or and?
Right, it's representing this, it's representing a different idea, but those are applications.
Okay.
All right. So we ready to go?
I think
Yeah.
so.
All right. Let's do a proof.
Okay.
You can't see.
There 1.
Are we doing all 12?
We don't have to do all 12. I'm definitely not doing 12. That's too big. But anyone from not 12 I'll do. I'll start with 1, and then you can just randomly pick the ones that you want. The only thing is, I think that these were put in a particular order so that you could reference the previous term and later ones.
Nice.
So I think they wanted that to be an application in developing this.
Mm-hmm.
So once I prove a theorem true, I can treat that like an axiom from there on out. Right?
Yeah, we did that in discrete math all the time.
That's
Your
how you build
geometry.
math. That's how
That's
you build
how you build a
calculus.
system of math,
That
right?
was
So
calculus.
have you done geometry?
Yeah.
So you did this in geometry all the time.
Mm-hmm.
Once you proved a theorem, then from there on out in all your proofs, you could use that theorem again. So once we proved theorem 1 and theorem 2, we could use theorem 1 if we want, just like we would use any of these things.
Right.
That can be a lot of information.
Yeah. It should be infinite information. Well,
Trying to
According to
calculus
what
works
was saying.
I think that's
alright,
the case.
prove. Yeah,
Goodle, yeah, I don't know if that was for any system
so
or if that was
here's
for
why-
particular
here's
systems.
5 actions. Prove
The
this.
particular
It's like,
systems it was true
prove
for,
this based on
our
everything
system
you
of
know.
math happens to be.
It's like, what am I going to pull this from?
See what I mean?
Either way, it's the same thing.
That doesn't
But-
sound like fun.
Obviously, you're obviously going to use them.
Can we zoom in a little bit to see the theorems better?
I don't know if this will zoom in this application because of a mode I'm in. Let me try that and then try this. Oh, there we go.
Nice. That's much better.
Yes, let's always do that.
Okay.
Well, I don't know if you
Go
can
one more.
change.
Oh yeah.
Alright. So first theorem, we're trying to prove that for all x,
Minus C.
not c of x implies c of x prime.
That makes sense.
Right? So we're doing a conditional proof here.
So we're going to have to use 3 and 4 probably.
So we'll start out with not c of x as a conditional premise, and then we need to come up with c of x prime. And which one gives us from, well, okay,
You could use number 3.
I'll just see if you, right, you just use 3 and you're done, right?
Right, because it gets you not.
Literally.
Oh, sorry.
No.
Sorry, I meant 4.
Number 4.
I looked at the wrong one with the wrong number. So,
Do you
remember,
have to use them both?
Right. Not
no,
of.
A implies B
And antecedent.
is logically equivalent to not
Not
B
A
or B.
implies
Not A.
not A. So maybe I'll rewrite really quick. I'm going to rewrite 4 this way.
It's
So,
not B and not
Rewriting
A?
4, I
No,
know that
not B
not
implies not A.
C of x
I know
implies
That's the
C of
contrapositive.
x prime.
Not B implies A.
You see how that's just rewriting this?
Yeah.
You are confusing me.
What?
Okay, contrapositive. If I know A implies B, that's logically equivalent to not B implies not A.
Okay.
Kind of weird too.
Yeah.
Yeah, but it works really well.
Yeah, I know that's. I've been using it.
This will make perfect sense to you. If I'm wearing shoes, then I'm not wearing socks is the same thing as if I'm not wearing socks, then I'm not wearing
Actually,
shoes.
you've already done this, yes. And it took me 30 minutes in one class to think I even have it.
Good? Okay, so we're going to use the contrapositive on number 4. Number 4 is saying not C of x prime implies C of x. So the contrapositive of that is not C of x implies not C of x prime. So you're good with this is just rewriting number 4. And this was our conditional premise.
Yep.
Da 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 da.
Well,
We're done.
We didn't even need to. Well, yeah, we did.
Any questions on that?
How'd you switch it though?
How did I switch what?
By using the contrapositive.
You're saying on
yeah,
7?
That's right. Contrapositive.
Yeah, I used the contrapositive on number 4. Maybe I should have written it this way to be more clear. Not C of x prime, and then we get not C of x prime, and then we get C of x prime.
Honestly, that helped.
Okay. What helps.
Next.
You good, James? Okay.
This next one should be pretty. So you assume CX.
Alright. Let's look at the next one.
Okay, so you're doing the same
For
thing
all
on 3.
x.
It's,
You're doing
yeah,
the
you do the
same
same thing
exact
with
thing on
3.
3.
We don't even need to do this one.
So skip 2.
It's the exact
It's the
same thing.
exact same thing on
Okay.
mine.
So let's do number 3 then.
What are you talking about?
They're saying theorem 2 is real easy, so we're going to go to theorem 3.
Oh, yes.
For all x, for all y, not C of
Oh,
X
this
plus
looks
Y
easy.
x plus y. They should all be fairly easy.
implies
Implies
not C Y
not
plus X.
C of y plus x. Right?
Mm-hmm.
Okay? So we're going to introduce not C of x plus y as a conditional premise, and we need to come up with not that as our conclusion. Now, we want to use a fact that we know that this plus is transitive inside of there, but we can't do that with that darn not on there.
Good, yeah.
Mm.
So just,
So, how are we going to get this?
okay, we're gonna use the fact that not X.
Contrapositive.
Contrapositive. We're going to use a contrapositive of association, which gives us, we're done.
That.
Oh, yes.
What?
Do you see that? What's the contrapositive of 1? Let's just write that out. That's saying not C
Y plus X
of y plus x implies
not
not C of x plus y. Now remember, the order that these, what we call x and what we call y is irrelevant. We could have called the y x and the x y, right? So when we did our universal instantiation of this, or universal, what does he call it? Specification of this, we could have called the x y and the y x, and then we just use this and we're done.
Yeah.
Make sense what I'm saying?
Yeah.
Mm-hmm.
Or you could just use number 1
What?
again and switch it around.
Okay.
I thought you
We'll
said
do this one a
last
little
night
bit
that
better.
You can't do that.
No, we'll do it. So we have this. You're good with that, right?
Yeah.
Okay. Now, separate from anything, I'm going to do universal specification. I always want to say instantiation. Universal specification on 1. Okay. Universal specification on 1. I'm going to say C of y plus x implies C of x plus y. I can plug in whatever I want for my variables when I instantiate it.
Remember, a variable is
Okay.
any number.
Yeah. Yeah, I know.
So you're good with that. Contrapositive of this is not C of x plus y implies not C of y plus x. Therefore, not C of y plus x. Because we already had that. Any questions there? Is it confusing that I was able to put this here?
Yeah, just a little bit.
Okay,
So if you know
so
it,
these
then
were
you
just
have
telling
schedule
us, this is basically saying for any two numbers,
Mhm.
if C, not numbers, for any two terms, if C of the first plus if you have C of the first plus the second, then you have C of the second plus the first. The fact that we use X and Y's in there, those are just variables to help us write it out. It has nothing to do with the X and Y's that we use in our actual proof. Right? I could have
Yeah.
used A's and B's here, and did all this with A's and B's, and we still would have been fine. Right?
But why did you go through all that work in the first place then? Like, why do you need that second step?
This one?
Yeah.
So this is my universal specification. We stopped doing this, so I only did this on my first proof, and then we stopped doing it, saying I'll just say when I'm using a definition, so we don't need to universally specify every time we do it. But if I were formally doing this proof, this would be one of the lines in there. If I was writing out every step.
Okay.
Right, because you just got rid of the.
For all.
Yeah.
This is true for any two I pick. Pick two. I pick Y and X. Okay, so plug it in for Y and X.
Right, so for your universal specification, then you took out the for all, right? And that's what you're saying. You
Yeah,
got for that
you
line.
get rid of the for all and you plug in for your variables. As a general rule, you just plug in the variable it already uses, but you don't have to.
Right. Okay.
As long as you stay consistent, that this one first and second and second.
As long as you do consistent substitution. Yeah. It's just like if I tell you that for all x, x is greater than 2. Maybe that's not a good way to say it. Maybe here's one that will help quick in your head. For all x, there exists a y such that y is greater than x. Right? So that's true. Oh, but that has a there exists, we kind of got to look at.
Oh yeah, it's
When did we get to
true.
this?
Just because you
I think
found
The next section. 4.3. We haven't even gotten through 4.2 yet, have we?
No, we haven't.
For all x, for all y, let's think about something in math that we know how to work. X times y is equal to y times x. Okay, we'll just do something simple like that. Right? So now, if, well, we won't say equals, let's just do implies. If, no, that's still hard. We'll write it something like this.
That's to work.
No, it's not an implication. X times y implies y times x. That's not a statement.
Oh, well.
X times y is
It's
even,
not, isn't it?
implies y times x is even. Okay, there's one.
Okay.
Right? If I know x times y is even, then I know y times x is even.
Okay.
That's true for any two x and y's you pick.
Right.
Notice it doesn't matter what numbers you pick here. And if I came along and says, well, is it true that if I know that y times x is even, do I then know that x times y is even?
I don't know.
Yeah, you just plug in your y for your x and your x for your y. This is saying, if I tell you that a times b is even, then you then know that b times a is even, right?
Yes.
This is one of the things it's saying.
Yes.
Saying if you know that the product of the two numbers is even, then the product of them when you flip them around is even.
Right.
Right?
Yeah.
So if the two numbers I pick are y and x, then the conclusion is it's true for x and y.
Okay.
Does that make sense?
Yeah.
And the x and y that I plugged in have nothing to do with how I wrote this here. This is just symbolizing here's where you plug in the numbers. All your x's plug in this spot, all your y's plug in this spot. Wherever you plug in for x, put it here and then here. Wherever you plug in for y, put it here and then here.
Mm-hmm.
So it's just making sure you plug in right. But you can plug in whatever you want. I can plug in x for y and y for x, and we're perfectly fine. Good?
Yeah.
Oh yeah. Was there anything else in the proof that we need to go over? Anything looks weird? Does it all make perfect sense? Good? Okay, pick another one.
So we have to just read the next one. Is that number 4 or 5?
We have another 4. You want to do 4?
Yeah.
So 4 says for all x, for all y, x plus y and not c of not c of x. No?
Yeah.
I keep seeing, oh, they're both, I was looking at 100, and it also had not c of x, right? Okay. Not c of x implies c of y, right?
Yeah.
Uh-huh.
Yeah, makes sense. Okay. So, let's do this one. So this one we have as our conditional premise,
We just have to get 5.
c of x plus y and not c of x.
Looks a lot like 5.
It's
Looks a lot like
Almost
5.
exactly just with the not reference.
Well, and a prime.
and the prime.
And the prime, right,
Oh,
but
but
we
not-
know exactly what to do with that.
Right.
Not c of x gives us what?
C of x
C of
prime.
x prime.
Where are you getting at?
4. 3.
3.
4.
You were right. It's from 4.
It's the contrapositive.
Contrapositive of 4.
Oh yeah.
So maybe we'll write it
Not
down.
contrapositives.
Universal specification on 4 and do the contrapositive all in one go. So we know not c of x implies not c of x prime, right?
Yeah.
Okay, so now
We have c of x.
combining these two, we now have c of x plus y and not c of x prime, right?
Yeah.
Because this implies this. So now we know this and this.
Right.
You good with that?
Yeah.
Since not c of x implies not c of x prime, then not c of x implies not c of x prime.
Yeah.
Alright, and then the nots go away, so we get c of x plus y and c of x prime, and then using 5 we get c of y.
Great.
Any questions there? All make sense?
Oh, these are almost easier from the other ones.
Huh?
I said these were almost easier than the other ones.
They are, pretty much.
Yeah.
So far.
Why
It looks
is
a lot
five
more
is-
complicated.
There's no proof by contradiction in these ones.
Yeah, we haven't had to do one yet. Who knows? Maybe there's one right around the corner.
Maybe we spoke too soon.
What one we on?
5.
5. You want to do 5 or should we keep going?
Well, we don't know if we're going to use these or not. I guess we don't.
Yeah, but we have the list that we can reference.
Yeah.
Remember, you can reference from above if we need. We'll do number 5 though. That one's easy.
And then number 11.
So we have not c of x plus y.
It's only 6.
Maybe this one will throw you guys for a little bit of a loop.
It's only 6.
Gives us
C.
not
Yeah.
c of x and not c of y. Right?
How is it 6?
It's a jump of 6.
Okay,
Yeah, it's still quite a jump.
6.
Two.
We start with not c of x plus y. Okay. What can we conclude from that?
Okay, so
The glare on the board is from that today.
Need to hang up more paper. Not c of x plus y.
You're going to use number 1.
Implies not
You're going to use number 1. Yeah, you're going to use that.
of y
Okay.
plus x.
So we can also conclude not c of y plus x. Okay.
And you'll probably use number 5.
I would guess
You'll
number
probably will, but you won't.
2. I would guess number 2 actually. Well,
Number 2. Quit second guessing. Apply the
Okay.
contrapositive to both these.
Oh, yeah.
What does this one imply?
Not c of x.
So from 8,
What?
look, using number 2.
Okay.
Okay, let's write out what number 2 says. Well,
Okay.
we have to write out twice because it says it 2 different ways.
No, let's just do it.
Okay, the contrapositive, so I'm going to universally instantiate 2 different ways.
Okay.
Here's one way I'm going to write it. I know through the contrapositive that not c of x plus y implies not c of x, right?
Yeah.
And I also know that not c of y plus x implies not c of y,
Of
Yep.
y.
Yep.
Yeah.
right? Not the first plus the second implies not the first. Not the first plus the second implies not the first.
So yeah, that's the entire proof right there.
So that's the entire proof. So combine these two with these two gives me these two.
Yeah.
Oh, yes. Oh,
And that's it.
yeah.
Yeah, easy, right? So that was 5, right?
I mean,
Wait. That's an implication, but you're looking for the and, are you not?
Okay. So we had not
We
c
don't know about
of
sure,
x
we can
plus
just go
y. We had not c
Yes,
of
but I
y
still wanna see
plus
you.
x. We can finish. So from these two lines, I can conclude this. You good with that?
Mm-hmm.
And from these two lines, I can conclude this. And from these two lines, I can conclude this.
And that's how you get your and.
Yeah.
peace.
Okay. Next,
Levi wants to do theorem 11 now.
theorem 11. Okay. So for all x, or you meant you personally want to do it.
Do you
For all x on all y. Oh, this one's tricky because we got
You
the
want
c
me to,
internally.
but it looks like it's a little bit trickier.
C of
No, we have
x
to do
plus
external.
y. Huh?
Yes,
Yeah.
Prime
you're saying the same thing.
Yeah. You just said it wrong.
plus y plus x.
What the?
So you have your
Crazy.
prime externally.
Okay, so
How do you even get your C external?
yeah, okay, so this one is interesting in that it's not an implication.
It's not an implication. How do you prove that?
So how do you prove something?
You just take the premises. Well, duh.
Yeah. You get
Well,
your
notice all the
premises
premises are implications. They never just tell us something. Like our other one, we knew that we had xqy or yqx, and we could always start there.
Yeah.
Notice that we don't have any axioms that give us a starting point, and we're trying to prove something that's not an implication. What on earth do we start with?
One
Well,
second.
you
One
can't
second.
start with
Do you
your
start
conditional
with-
premise, or can you?
Why are you locking?
Because it's supposed to be obvious and we're not seeing it.
You just start with the premises.
Okay, which premise should we start with?
1,
Okay.
2, then we go to 3.
So I know if I have this and I have this, but what do I have?
That.
So where could we possibly start?
Theorem 10.
You can. You specify your thing.
I specify this, I just say, let
No,
this be true.
That's not true.
Prove
That's
it.
not right.
Not
That's not right.
Da, 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 da.
theorem.
Done.
Who's
Easy.
gonna get it?
Say it's not true.
And show that.
It is.
Contradicts itself.
Proof by contradiction.
Obviously.
Obviously, the thing that we haven't had to use yet.
Yeah.
I don't have to use proof by contradiction on any of these. Wrong.
That's
Okay.
4 you have to.
So assume that this is false, and show that at least
prove
a
that it's
possible
true.
worldview. Therefore,
Yeah.
it's true. So we start out with not c of x plus y prime plus y plus x. Right?
You
Yeah.
said X plus
That's
X.
what I mean. I don't
Y
get
plus
it
X.
sometimes, dude.
Yeah.
Y plus x.
I think he's working so fast he can't catch up with understand.
Okay.
It's still.
So now we've got a lot of, and this is by way of contradiction. This isn't a conditional proof. Right?
Mm-hmm.
Okay, now we got things we can do with that, right?
Yeah.
But all we gotta do is come up with a contradiction.
You use number 4 first.
Use number 4 first.
Yep.
So you're saying you want to conclude from this,
That's just.
but we don't have number
No.
4.
Wait a minute.
We definitely have to use one with a plus in it.
So number.
So we're kind of stuck with 1 or 2. You want to use which one?
number
No.
1.
You want to use number 1? So
Yeah.
you want to change the order of those bad boys?
We want to do 2. We wanna
Probably
do-
not. Yeah, 2's the only one that gives us something new to work with.
Yeah, that's right.
Alright, so what does it that gives us?
Positive.
That gives us not. Now Now, maybe your idea isn't bad in that flip these orders so that we can use 2 again, right? So maybe I'll write both those out real quick. So not that, we also have this, C of
Y plus X prime.
X, thank you.
How do you do with the prime?
Just like any other term.
Y plus X plus X plus Y prime. Okay, so we have it both ways using number 1.
Mm-hmm.
And now we're going to get information for both these using number 2, right?
So contrapositive on 2.
So contrapositive on 2, what's this one going to give us?
Not.
No?
Not X.
Oh yeah, it is a not, sorry. You're right. Not C
Not X.
of,
X
Prime.
we're applying it to this one.
X prime.
Oh, X plus Y prime.
X plus Y prime, good job. You follow that?
The first.
We have X, we have the first plus the second.
Okay.
Not the first plus the second gives you
Okay.
not, or gives you the first, not the first. So it gives you not the first.
Okay. Okay.
You follow that?
Yeah.
Yeah, but can't you have not the second too?
Well, yeah, but you have to use one first.
Yeah, but either way.
And so use one to use the associative property, and then we can do the same thing and we can also conclude not C
Y plus
of
X.
Y plus X.
Okay, we're
Yeah.
looking
We don't
for
need that
contradiction, guys. Remember
Right.
that.
Yeah.
So now we can just write Y plus X, right?
Yeah.
Now we still know that that stupid prime is giving
Use
us
4.
problems.
Use 4. So now you can just say C of X
Wonderful.
plus Y.
So using 4 on this, we're able to conclude C of X plus Y.
Yep.
And using number 1 on this, we can say C of Y plus X.
Oh.
And now combining these two, we have C of Y plus X and
Not C of Y plus
Yeah,
Y
X.
think
plus
so
X.
like
Crazy.
general and then specific and then general specific.
Yeah, Z-man's about.
Yeah. Then you get clear picture.
Good. What time is it?
Whoa.
Like 9.
Jeez.
Something like that.
Yeah.
Oh, go.
It's
'Kay.
8:50.
Let's crank through what I've got up here real quick, and then we can do examples galore. Okay? Because we already
Examples of the Lord.
we've already
He uses straight logic.
done a lot of these to help us get our footing. So back to 4.2. So 4.2, the big idea is
Sorry, before
we started it last time.
Yeah,
And now we're gonna come do it real quick. And since you all read the chapter, there's no point even doing this, but
Right.
we're just gonna do it.
Right.
It's pretty fun.
Uh,
Alright, interpretation. Okay, so
Sentence P.
remember the interpretation is how we determine whether or not it's true or false.
Right.
Yeah.
So sentence P, remember, so P is what our interpretation is gonna be. It has to be a sentence because it's gonna be true or false.
Yes.
So remember, we
Sentence
turn
B
formulas
is
into
our
sentences.
interpretation.
We turn formulas into sentences. Here's a formula. X is less than 3. Here's a sentence. There exists an X such that X is less than 3.
Well, can you?
Or we could have just said 2 is less than 3 and gotten rid of our free variable, or we could have bound our free variable. But we can't have a free variable.
And don't we define formula with atomic formula? And-
Yeah,
And a bunch
the
of
formula
others?
was one with a recursive definition.
Yeah.
Starts out with atomic formulas, and then you can AND them together, you can OR them together, they imply each other, you can not them, etc. You can add existential, or you can add quantifiers on them.
And what was the definition of atomic formula?
He didn't give a precise definition of an atomic formula.
Of course.
So you'd have to go look at what they were, but
Essentially the chunks.
Chunks of what?
No, it's
The chunks is
basic.
a
it was
Just
either
It's a basic formula.
It was
Atomic.
a term, it was a predicate together with the appropriate number of terms.
Right.
Okay, so interpretation. So sentence P is an interpretation of some formula Q with respect to domain D. So from here, before we've always just been assuming the domain based off the problem.
Mm-hmm.
If my formula was about numbers, you knew the domain was numbers. The domain is just what you can plug in there. When I say x less than 3, jeez, there we go. X less than 3, it's understood that the domain is numbers.
Right.
Uh-huh.
We're dealing with humans.
Yeah, if I said A loves B, then you know that
People.
we're talking, well, at least A, because we only know A to love, so whatever the set is, probably should have come up with a better example. I should have said A married B, or something like that, right?
Yeah.
Doesn't matter, you get the picture. So we've been assuming our domain. From here on out, when we make an interpretation, we need to say exactly what our domain is that we're talking about. Okay? So, continuing. So, sentence P is an interpretation of Q with respect to some domain D, if and only if P can be obtained from Q by substituting predicates and operation symbols defined on D for predicates and operation symbols, respectively, of Q, and substituting elements of D, in other words, constants, substituting elements of D for constants and free variables of Q. So, we'll see examples and we'll go over this definition here because it's got a lot going on. So we'll do examples and I'll point out in the definition where we're seeing it take place. Okay? So let's just look at this example. So here's some formula key. For all x, for all y, xpy implies not ypx. This is one that we just used.
Yeah.
And we were saying one of the interpretations, we'll get to that one. I guess I did the parent one first. So one of the ways I could interpret this P is the parent of. And I could make my domain all people. Okay? So make my domain all people, and I'm going to interpret P as the parent of. So how do I interpret this then?
Yeah.
For any two people, if X is the parent to Y, then not Y is the parent to X.
Right.
There's an example of an interpretation. Okay? So in that interpretation, notice I replace my predicates with predicates that make sense on my domain,
Yeah.
D.
Right.
So that's what we're saying up here, is saying it is a substitution if and only if P can be obtained from Q by substituting predicates and operation symbols defined on D for the predicates and operation symbols respectively of Q.
Right.
That's what we did right here. These were the predicates on Q. We replace them with predicates on D as the parent to.
It's like sentential interpretations with predicates.
Wait.
All sentential interpretations were interpretations.
Right.
Just like all squares are rectangles.
Yeah.
But we just want rectangles. We don't always want to just talk about squares. We don't always just want sentential interpretation. It's too strict. We want more freedom.
Well, then we can do more.
We want to preserve more structures, maybe a better way to say that. We don't want to throw all the structure out the window except sentential connectives. We want to keep lots of structure. Anyways, so here's one way. Let's look at another interpretation of Q, this time using it how we did before. I'm going to make D positive integers. That's fine. And now I know, for any two numbers, or for any two positive integers, if x is greater than y, then it is not the case that y is greater than x. This is another interpretation on this. Notice I replace my predicate with an appropriate predicate. Greater than is a predicate on the positive integers.
No, it makes sense.
Right?
Mm-hmm.
So here's two very different interpretations of the exact same sentence, or of the exact same formula.
Right.
Formula, two interpretations.
Just using respectively to their domains.
Yeah, and I specified exactly what their domains were, and the predicates have to make sense on their domain.
Yeah.
And these ones don't have operation symbols, but if I had operation symbols, they also need to make sense on the domain.
Right.
I know what it means to add positive integers together. I don't know what it means to add people together. That's not a defined operation on the set of people. Okay, so now let's just look at another example. Here's our, notice in this formula it was also a sentence, right?
Yes.
So that doesn't have to be the case, it just has to be a formula. So here's a formula that's not a sentence.
Because
Okay.
it's not the universal.
Because we have free variables.
Oh, right. X and Y are free.
Yeah, x and y are free, z's bound. So when we do our interpretation of this, we need to replace x and y with elements of our domain. So let's look at it real quick. So if I have xpy implies for all z, xiz implies zpy. Okay, that means whatever it means, who cares? I mean, you already have intuition for what this means because of our proofs, but let's just do an interpretation of it now. Okay? So I'm going to make my domain, again, all nuclear families. You understand what a nuclear family is?
No.
No.
Just the mom and the dad and then any kids that they have.
Oh, okay.
So no broken homes. Once it's a divorce, it's not a nuclear family. You can't have all sorts of weird mixes. Okay. So Jack is parent to John. So notice, is parent to is what I'm replacing P with.
Yeah.
Okay? So is parent to is my predicate for P.
So
And
because,
is sibling of is my predicate for I.
alright, is because X and Y free, is that why you put specific names?
Yes, so since X and Y are free variables, in my interpretation, I have to replace them with elements of my domain. My domain is nuclear family, so I have to pick two people in a nuclear family.
Okay.
I wrote nuclear families, I meant people in nuclear families. Sorry.
No.
Right. Okay. So, Jack is parent to John implies for all Z stays because it was a bounded variable. So, Jack is parent to John implies for all people, if John is a sibling of that person, then Jack is parent to that person. Right? Jack is John's dad, therefore if Z is John's sibling, then Jack is Z's dad as well.
Makes sense.
Right? That's interpretation of this sentence,
Yep.
or of this formula. So let's go over our definition again to see what was happening here. So we said, if and only if P, that's this one, can be obtained from Q by substituting predicates and operation symbols defined on D for predicates and operation symbols of Q. So we did that, we replaced is parent to for P and is sibling of for I. And substituting elements of D, namely Jack and John, for constants and free variables of Q. We didn't have any constants in Q, but we did have free variables X and Y. So we need to substitute elements of our domain for X and Y. Okay?
Yep.
Let's look at another interpretation. This time I'm going to pick D to be positive integers. I'm going to pick P to be greater than. I'm going to pick I to be equal to. Okay? So now it's the same.
4 is greater.
I need to pick two elements for X and Y. I pick 4 and 1. So 4 greater than 1 implies for all Z, if 4 is equal to Z, then Z is greater than 1.
This actually helps your brain understand what a free variable is.
Yeah.
Or like the purpose of calling them out, you know?
So
Recognizing free variables.
now notice that when it's interpretation, that just makes up we can call it true or false.
Yes.
We don't have to pick true interpretations for it to be an interpretation. So here's an example of a false interpretation. Pick 1 for X and 9 for Y. And keep my predicates the same. So here's another interpretation. This time I made D real numbers because why not? Okay? So 1 greater than 9 implies for all Z, if 1's equal to Z, then Z is greater than 9. That's a false sentence. It's a false interpretation, but it's still an interpretation. When we say false interpretation, that sounds bad. Because it's like we failed at interpreting. It's a valid interpretation.
But
So
this
then we can
is
determine if it was
false.
true or false. But it happens to be false. Notice our initial formula doesn't, we can't call this one true or false.
Right.
So when you have a formula, you can't necessarily call it true or false. But in interpretation, we can always call it true or false.
Right. Formulas and sentences aren't.
So the interpretation doesn't make it true. The interpretation makes it so you can determine if it's true or false. That's what interpretation does. Make sense?
Yeah.
Good.
Can't you do interpretations with literally true and false inputs?
Yeah.
Right.
That's exactly what you're doing when you do Boolean algebra. You're looking at true and false as your domain. That's what Boolean algebra is. Yeah. Okay. Let's look at another example. So
Oh, we already,
X is a city. Yeah, we did this last time. That's what I was saying. But
yeah.
now I'm gonna hurt to go over it again, even though you guys are all pros. So X is a city, and X is larger than San Francisco. So first thing we need to do is symbolize that into a formula, right? So we know we're applying some predicate to X, and some other two-place predicate to X and a constant San Francisco. So this is just a symbolization of this, right?
Yeah.
And now we're going to do an interpretation. Now I don't have to do this step. I don't have to go from this to this. We're able to read this sentence and see that we have a free variable X, a predicate, and a two-place predicate, and a constant.
Yeah.
You could have just seen that, and you could have come up with an interpretation of this sentence without doing this, but we did this first. This isn't a sentence, sorry. I meant in the English way, a sentence, not in here.
A sentence can't have free variables, right?
A sentence cannot have free variables. A sentence is true or false. And if it has free variables, you can't turn it
Is
into
a constant a free variable? No, it's not variable. Okay.
No.
let's do this question.
Yeah, there you go. Okay, so here's some symbolization of the sentence. We have some predicate is a city applying to X, and some two-place predicate is larger than applying to X and some city, a constant. So let's do our interpretation now. So we need pick a domain. This Z right here, that means all integers. It's a common domain to use for interpretations, so we have a special symbol for it. In this case, it's a Z. So that means all integers. So my domain is all integers. So I need to pick a predicate that makes sense on integers. I pick is positive. Is positive is a predicate that makes perfect sense on the domain of integers, right?
Mm-hmm.
And I need to pick a two-place predicate to replace is larger than. Well, there's a natural one for that. Is larger than, or greater than symbol, right? So here's a predicate I chose. Is positive and greater than. And is just and, that doesn't change. Now I have a free variable x I need to replace, so I pick the number 2. And I have a constant a that I need to replace. I pick 19. 2 is positive and 2 is greater than 19. That was my interpretation.
Nice interpretation.
Let's go over the definition one more time, because this is the first time we replace a constant, and I think you'll officially have the definition. So, P can be obtained from Q by substituting predicates and operation symbols. We haven't done operation symbols yet, so we're not done yet with the whole definition, but continuing. So, I replace my, let's see, restart. So it is the case if P can be obtained from Q by substituting predicates and operation symbols defined on D for predicates and operation symbols of Q. So we did that by doing the is positive and the greater than for is a city and is larger than. And substituting elements of D for constants and free variables of Q. My constants and free variables in Q were X, X, and San Francisco.
Right.
So I replace that with 2, 2, and 19. Alright? Alright, let's look at another one. Okay. So, let's see. I'm replacing is a city with is a man. Well, let's look at my domain first. My domain is all people. Okay? I'm going to replace is a city with is a man. And I'm going to replace is larger than with is larger than. Because it makes sense for one person to be larger than another person, right?
Mm-hmm.
Okay. So, and I'm replacing X with Frank, and I'm replacing San Francisco with Jack. So Frank is a man, and Frank is larger than Jack. There's my interpretation. Good?
Yeah.
Okay. Let's look at another one. So this is also one we looked at. It's this exact same one, but I put there exists in front.
Right.
So now it's a sentence.
No.
So yeah, now Q's a sentence. So there exists X such that C of X and LXA. Right? And then I just rewrote these exact two interpretations, just adding there exists X in front. But notice now, X isn't a free variable in this one.
Yeah.
Frank is out of
So
the picture.
now, we don't have 2, we have X still. So instead of 2 is positive and 2 is greater than 19, we have there exists an X where X is positive and X is greater than 19. And instead of Frank being the large guy, we have there exists an X where X is a man and X is larger than Jack. Make sense?
Yes.
How having that there exists changes how we can interpret these sentences and what you do with free variables versus bound variables.
Yes.
Yeah, I think you guys are getting a pretty good hand for this. So that's like the one with operation symbols. So here's Q. Q says for all X, for all Y, X plus Y equals Y plus X. What's the interpretation of that? The exact same thing, just add a domain of Z. When I do empty quotes like that, that means just look at the thing above, and I didn't want to rewrite it.
Okay.
So this exact thing, but now my domain Z, that's one interpretation of it. Another interpretation that we could have done is keeping it all integers, and we could have just replaced the plus with the times. That's interpretation of it.
We're replacing operations.
Yeah, so remember we can replace operations and predicates with operations and predicates.
Right.
So I replace plus with times, that's perfectly
But
fine.
you can't replace
As
a
long as
predicate
it
with an
makes sense,
operation.
right?
Oh yeah, you can.
No, those aren't the same thing. X is less
Oh, yeah.
than 3 is very different than 2 plus 3.
Right, because 2 plus 3 is
This is a term.
Right.
This is
A predicate.
a predicate. And notice this can never be a sentence, but this could be. 2 less than 3, that's a sentence. So predicates and operations are not the same thing. Operations take terms and combine them to give you terms. That's what they do. It's always just a term, it's never a sentence.
Or, quick question, could there be an operation that splits a term?
An operation that splits a term?
Yeah, instead of combining, or is that a thing?
Yeah, if you want to, kind of. So the first one that came to my mind is like the square root operation. What's the square root of 4?
Right, plus and minus 2.
Plus minus 2. So that's really, what are the solutions to the formula x squared equals 4? Is
Right.
what that's really asking. We just say it, we word it badly, because really, you define square root as a function, and a function takes, you define it as a real value function. It takes one input, spits out one output. So we would say, because oftentimes when you use like a quadratic equation, you say plus or minus the square root of,
Right.
and the square root's always positive. So you see what I'm saying? So square root by itself always references a positive number.
Okay.
So that one doesn't really work. I don't know. I don't think so. I can't think of any example where that's the case. Every operation I can think of, it ends up returning a single term.
Well, if you think of an operation like a function, then that makes sense.
Right, I think every operation could be captured by a function. I think that is the case. I wish I could have gone that on camera. Alright. Moving on. Okay, and then another interpretation of this is just right here, right? Replace plus with divide and we're good?
Yeah.
No. I won't yell no because my baby's asleep in the other room. No.
Because it's not
Right?
a valid interpretation.
Because our domain is z, and x divided by y is not necessarily a member
And
in
the
our domain.
operations have to apply to the domain.
Yes, the operation has to be closed on the domain.
It
Has
doesn't
to
say that.
return terms in the domain. They specify it later, even in case there was any ambiguity in the definition. So the author takes
But
the
the
time to,
definition shouldn't be ambiguous at all.
well, defined on the operation. We haven't yet talked about what it means for what exactly an operation is, or what it means to be
Yeah,
closed.
why not?
Well,
Don't they
I'm
presuppose
guessing that we're going to have to define an operation in terms of a function. Like I'm thinking about the successor function, and we're working up to a foundation where we can do that.
So, pretty much impossible.
We're not ready to define
So how
functions
did
yet.
they do that in the beginning? Like when they came up with all of this?
Well, they came back and came up with all this. Right?
How
So they did it all and then came back and built the foundations for it?
I
That
would
make sense.
guess so.
That's a very common thing. So calculus is one that definitely went that way. So Newton did not use the definition of a limit that we use today. His was very imprecise. It was very vague what he was talking about relative to today's term. Cauchy's the one that went, lots of mathematicians did, but he's a very famous one that went back and made it all rigorous. Because there's very subtle notions that were being captured there that there's no way Newton could have known. So that actually happens all the time. It goes back and becomes more rigorous. Like, it's exactly what happens with geometry, for example. Euclid had his rough and tumble postulates and axioms, and they proved what they proved. We still use everything that he proved. It still all works in our system of geometry.
Precise.
We just went back to more precise axioms and what it was he used. And even what we're doing now, redeveloping logic, I mean, this is not what Aristotle wrote in his, what's it called, organon, something like that.
Did he write a textbook on logic?
Organon? I think that's it. Yeah. Yeah, Aristotle, well, I'm sure people before him did it, but he's the one credited with formally writing down logic. He's pretty much the father of any field you want to go back far enough in. To some extent. Definitely with biology. That's where he spent a lot of his time. We had a lot of passion for. But he's even the father of science to a large extent. He's the one that was arguing with Plato that no, if you want to talk about what's real in this universe, you need to go back to empirical data, inductively reason on that empirical data to come up with assumptions, and then look at the logical implication of those assumptions. That way of thinking about coming to knowledge of our universe is exactly what Euclid talks about, or not Euclid, Aristotle talks about. People way overestimate Francis Bacon's contribution to science and completely overlook what Aristotle did.
Well, I hear Aristotle. Everyone makes fun of Aristotle for.
Everyone makes fun of Aristotle. They first claimed that he thought that you could come to conclusions about the universe just by thinking about things. Now, he never said that. That's Plato's perspective of the universe. That's not Aristotle's perspective of the universe. And then one of the other things that they were concerned for is he said, heavier objects fall faster than lighter objects. Right? And then he gets mocked for never going out and really testing this. When you look at everything he did, if something appealed to his intuition like that appeals to your intuition, any person who wasn't explicitly shown otherwise would probably think that. He didn't bother going out and testing it. Most of his time was spent in biology and classifying things. That's where he spent his time. So physics wasn't one of the areas that he spent time, and that's what we're going to ridicule him for. It's like me ripping into you because you're not a pro computer science. Like, that's not what you do. Maybe you did a little bit of it on the side once, but your focus was.
Well, I heard they got mad at him because he said every element is either water, earth, fire.
Yeah, so water, earth, fire, air, and then the fifth one, I don't know if they call it ether, and that's how ether got in there. Something like that. But even just water, fire, earth, and air, that predates him, first of all. So there was already physics built up out that way, and people trying to argue that everything's made out of fundamentally the same material. And some people thought that it was fundamentally water, other people thought it was fundamentally air. Those are the two major ones I know of. I don't know if there's other people who thought it other ways. So he was adding to a developed notion that existed in his day. And yeah, he used his elements to come up with a theory of gravity, so obviously I'm not going to capture it in 10 seconds, but really briefly speaking, he's saying, look, fire's out here, then from fire you have air, then you have water, then you have earth. Right? So you stand on the earth, and then there's water on top of the earth, and then there's air above the water, and then the fire's out here. Yeah, look at the sun, look at the stars. Fire's out here. And so fire wants to be out here, air wants to be here, water wants to be here, earth wants to be here. That's why if I take water and I drop it right here, it's going to fall. It's not going to go through the ground, but it's going to fall and sit right here. But it falls through the air, and if I were to light a fire right here, the fire goes up, and it tries to get higher than the air.
That's actually observable fact.
Now that's a really dumbed down notion of what they were talking about. If you were to read through exactly how they're making these arguments, you're going to say, yeah, that makes perfect sense. I mean, there's a reason that
There's
thought
a
it.
lot of stuff that they didn't know about.
There's a lot of stuff they didn't know about, but there's also a lot of stuff that they did know about that people, for example, Aristotle, we don't know if he was the first one to prove it, but he's one of the people that proved the earth was round. He knew that. And we pretend like that knowledge was somehow lost, and people in the Dark Ages thought the earth was flat, blah, blah, blah. No, that's not true. Everyone knew that the earth was round from Aristotle on. Not everyone, but society as a whole. Yeah. Educated people living on the earth knew
Why were
Aristotle
people
on.
killed for or house arrested?
That's
Galileo.
So you're talking about Galileo, which
Had to do with the church, didn't it?
yeah, it had to do with Ptolemy's model of the universe.
Mm-hmm.
So when you have crude instruments for measuring, it roughly looks like you have the Earth here, and then the moon goes around the Earth, and then the sun goes around out here, and then the planets are going around out here, and then the stars, they don't rotate. The Earth spins, but the stars stay where they are. Or, and remember, well, I can't say remember because you guys don't take physics, but in physics, velocity is relative. It's just as valid for me to walk through this room and say the whole room is moving that way as it is for you guys just say, no, I'm moving that way.
Right.
Those are logically valid ways of viewing the universe. You can't say one is right and the other is wrong.
Mm-hmm.
And we now know that today. That's Galileo's theory of relativity. It's one of our basic assumptions of science. But so whether the Earth is spinning or these things are moving and the stars are holding still and the Earth's spinning, or whether the Earth's holding still and everything else is moving, kind of irrelevant, right? But, so roughly speaking, this was the Ptolemy model of the universe. Time went along far enough that the church accepted the model and gave their biblical arguments for how the Bible supports this model. And so, I can't remember the name of the guy who first suggested that. No, actually it was the sun, and then you have the planets going around, how they're going around. But Copernicus proved it. So Copernicus took the time to do all the charting, and you can read through his proofs, and I don't recommend you do because it's before analytic geometry, and reading math proofs before analytic geometry is a pain in the butt. But you can. So he does all his charting, and he does his geometric proofs to prove that, no, actually the sun's at the center, and everything's moving around the sun in relatively circular motions. It took Kepler to find out, no, actually they're ovals, but
Eclipses or
ellipses, yeah, ellipses. So that's what that was about. So Galileo knew Copernicus's work and said, yep, Copernicus is right. That's what got him house arrest.
I say he's right.
Yeah, by agreeing with that model.
Oh, that everything doesn't revolve around the Earth.
Yeah, that the Earth's not the center of
Universe.
the universe like Ptolemy's model had it.
Right, that makes sense. So it wasn't about the Earth being round.
No, it had nothing to do with the Earth being around.
So even Columbus knew the Earth was round.
Columbus very much knew.
Oh yeah, he was
the
trying to
Earth
get to
was
Asia.
round.
That's right. Okay.
Yeah, he made calculations that made him suspicious that the Earth was actually not as big as people thought, something to that effect. And so people were thinking, no, it would take you going 20,000 miles or whatever it is to get from England to India. And if you look at the maps that they had at the time, I mean, it is not anything close to globe that we have now. So he had some maps or did some charting of his own or something that made him suspicious that, no, that was actually half the distance and it was only 10,000 miles. And he went 10,000 miles and he hit land, just like he thought he would. So, I mean, there's a reason he thought he hit India. He's not a dumb guy. I mean, you don't go round up some people and guide a ship all the way that far and be a dumb guy. We like to downplay how smart people in the past were, and we like to think we're so smart, but oh my goodness. We're so uneducated relative to people in the past as a general rule.
As a general rule, really?
Yeah, Euclid's Elements was a standard textbook for learning mathematics for over 2,000 years. I would bet that a typical high school graduation at the academy has 3 students who could do the second postulate. Maybe 3 students who could do the second problem in the book. And these are students who have had how many years of math education?
12.
And they can't do the second problem in the book, the standard textbook that's been used to teach people math for over 2,000 years.
What's the second problem in the book?
If you have a line segment and a point not on the line segment, there exists a line segment of the same length terminating at that point. Or essentially, if you want to think about it as constructing it, construct a line segment from this point that has the same length as that.
It's actually so fun to do that.
Yeah.
To prove that?
Yeah, it was
Yeah.
very fun.
Oh my word.
I have to.
That was fun.
Yeah,
We'd have to use postulates. I can't do it in
It's like you can
Uh,
create form.
10 seconds because I have to reference everything I'm using.
Right.
And I'd have to use the previous theorem, which is proving that equilateral triangle exists. But after an equilateral triangle, that's the second one. Not a chance. You spend way more time nowadays just entertaining yourself than you do rigorously learning something. And even by a lot of, if we use like a philosopher's standard, most of the stuff you think you know, they say, no, you don't.
Right.
You say the earth goes around the sun, they say, how do you know that? My teacher told me. Oh, they did? How did your teacher know? Their teacher told them.
So you're saying an average person might just have read the proofs on why the Earth revolves around the sun?
Yeah, if they wanted to know it, that's what Galileo did. He didn't say, Copernicus said. Take that, church.
Right.
No, that's not how that happened.
Why was reading proof so hard? Like, what's the difference between before analytic geometry?
So analytic geometry is what combines a coordinate system with geometry. So you can start putting numbers to it. And that makes talking about a lot of things much, much easier.
Because it's not so general?
Just because it's very helpful. For example, then once I bring analytic geometry into it, I can now always talk about the distance between 2 points.
Mm-hmm.
And that's one thing that's often useful to be able to mention when you're
And you
doing your
can talk
proof.
about the distance.
But then you could also talk about, so it combines numbers and geometry. So you can start capturing, here's what essentially it allows you to do. You can start capturing geometric relations in equations. And you can start using equations for things.
And you could
So
do-
now instead of talking about this line, I can now talk about y equals 2x. And if I'm doing some physics that relies on y equal to 2x and I'm messing with this formula, that's a lot easier to use than this line.
And how would you
And so-
use the line?
Huh?
How would you even use the line?
Well, I mean, it depends on the proof. I'm just kind of talking on the fly, but like reading what he did and Galileo, he's an especially hard one to read because he's still before it. Reading some of their proofs, so like one of the things Galileo proves is that, now I can't remember the relation, but basically he's proving that blowing up the size of an object doesn't maintain its structural properties like you might think. So just because I can take a piece of wood and make it this thick and this long, so say that that's a stable configuration for a certain type of wood, that doesn't mean, okay, then I can scale it up, make it twice as long and twice as thick and we're still good. And that I can scale it up twice as big and twice as long and we're still good. Because one of the things you might be interested in is I gotta build a cathedral and I need a plank to go across this. Is it really feasible to just use longer and thicker wood to just keep doubling each time, or do I have to increase by more than that? What's it proportional to? And so he proves, I think it's proportional to the surface area as opposed to just the thickness.
Mm-hmm.
And that's a proof that he does. And that is even a simple relation like that is, it was a lot to get through. And a lot of losing track of what he was saying and going back and rereading. Very hard to read. If you just try reading one proof, you completely understand what I'm saying. It will pop out at you that this is so hard to understand. And when you finally do understand it, you'll be like, that seems like a really simple concept for all the explanation that just went with it.
So it was probably pretty difficult.
Well, difficult for us because we're used to particular things. It was more difficult. I mean, the reason that Descartes came up with analytic geometry was because he thought it was so tedious doing geometric proofs the way that people were doing geometric proofs. And he had very poor health, spent a lot of time in bed. He didn't have a lot of time to do it. He needed a faster way to do it. Analytic geometry. Because a lot of geometric proofs, it just requires you to have that one epiphany that you need to have to finally, it all comes together. Whereas with numbers, a lot of times you can just kind of throw the numbers in and start calculating things and determine your answer that way. Or just get some big equation, who cares if it's messy. So, anyways. Let's finish these last ideas.
So we just got done with.
So we got done with this one and we understand why you can't use divide.
Yeah.
Okay, so moving on to this one. There exists a y such that x plus y equals 2. We're going to do an interpretation of that. X is a free variable, replace it with something. 2 is a constant, replace it with something. Replace the predicate with something,
Oh, right.
and we're good. Alright? Okay. So there's some examples. The section 4.2 has a lot more examples that I was going to do after this, but we don't have time for, so we'll just let be. But you can go through and read through all the different examples. Let's touch on these ideas and then we'll be done. And I'll briefly say how you do each one. Okay, so now we have an idea of an interpretation. What do we use interpretations for? We use them for determining if something's universally valid, if something logically follows, if there's an invalid argument, and if the formula is consistent. and this formula is going to be like a conjunction of axioms. So determining if a set of axioms is consistent or a set of premises is consistent. It's just going to be a big conjunction. So let's go through each one. Universally valid. This is like a tautology. A formula is universally valid if and only if every interpretation of it in every non-empty domain is true.
Well, how do you show every? Oh, you just can't find false
Non-empty
or what?
domain, what is that?
You can prove by contradiction.
Yeah, so let's talk about this non-empty domain real quick. Why do we say a non-empty domain? So we don't want you picking to do it on an empty domain of objects. So we did V on Z.
Because if you deal with
We didn't have an empty
non-empty-
domain.
If you use an empty domain, it's not defined.
Well, the reason that we want it to be a non-empty domain, well, you can say any predicates define on an empty domain if you want, but we want notions like this to carry through. If we know that H is true for every object, we want it to be true for some object. So we specify a non-empty domain because we don't want to care about empty domains. I mean, in short, where are we going? We're going to be going to math, where we're talking about on the set of points if we're talking about geometry, or on the set of numbers if we're talking about algebra. But we want notions like this to carry on. We want to know if something's true for everything, then there's something that's true for it. And we want that to be a generalization that we can do this as a
Right,
general.
so if it was empty, then you wouldn't be able to do it for that
Right, if it's
specific
empty,
one.
then anything's true for every object in there,
And you
because it's
can't go
empty.
for-
But you can never conclude that anything's true for a particular object because there is no object.
Right.
So it makes all our universal quantifiers, any universal quantifier with a predicate,
It's always true.
always true or vacuously true, and it makes any existential quantifier with a predicate
False.
false. So it becomes like a useless system
Right.
once we have an empty domain. So that's why we say in every non-empty domain. Logically follows. A formula Q logically follows from a formula P if and only if the conditional P implies Q is universally valid. So universally valid is basically a tautology, and it logically follows if P implies Q is a tautology. Make sense?
Mm-hmm.
Okay? An invalid argument. An invalid argument is basically we're showing it's impossible to get the conclusion from the premises.
This is proof by contradiction. No. Or sorry.
Well,
This is
the thing
finding-
you're thinking,
An example.
yeah, it's going to be one of the ways we show an argument is invalid is with a
Counterexample.
counterexample. That's exactly right. So,
But you don't necessarily need a counterexample to prove it's invalid.
correct. So, well, I don't know.
Either way.
Because,
If you
Let's
prove it's
just
invalid,
read.
then you'll find the counterexample.
so an argument is invalid if and only if there is an interpretation in some non-empty domain which makes its premises true and its conclusion false.
Right.
Right? That's how we know it's impossible to prove something.
We've already done that.
We have done that. That's exactly right. We have done it. Now we just are doing it when we have this for interpretation instead of sentential interpretation.
What was the definition of sentential interpretation?
We,
All those weeks ago.
You have to keep all of your.
you just have to preserve basically the
The form.
sentential connectives.
Yeah.
You can
just
switch
the
atomic
sentence.
sentences
Right.
or atomic.
That was the only structure.
But that was without predicates, right?
Yeah, there was no predicates, there was no quantifiers,
There's just atomic
there was
sentences.
just parentheses, sentential connectives, and then we had letters representing entire sentences. So we assumed if I had something like this before, then B was a sentence, C was a sentence, and B and C was a sentence.
That's right.
So we were talking about very,
Very broad.
not broad, we were very much restricting ourselves to things that we could talk about. We could only talk about applying true functional sentential
What I'm saying
connectives
is
to
It's
sentences.
just like each term was an entire sentence, not.
Yeah, but notice it was also a sentence. We couldn't talk about just formulas. We were always talking about sentences.
Right.
So it was very strict in what we could talk about. We can only talk about things that we could talk about as true or false. Now we're talking about a formula. A formula Q. This is no longer something that is a sentence. A formula Q logically follows from P if P implies Q is universally valid. You see how we're talking about a much broader thing now than just sentences? We now can talk about formulas. Okay, logically follows invalid argument. An argument is invalid if, oh, we already said that, if there's an interpretation in some non-empty domain, which makes the premises true and its conclusion false. Right? So, do an example real quick. If x is even, then x is greater than 2000. Let's say I want to prove that this argument is invalid. I need to find an x that makes my premises true and my conclusion false.
2.
2000.
2 is even, and 2 is greater than 2000? No, doesn't work.
2001.
2001 is not even. So that's not a counterexample. I need to find an x that's even. I need my premise to be true and my conclusion to be false. So an argument is invalid if it's possible to find some interpretation that makes the premises true and the conclusion false.
Right.
We also call that a counterexample. Find a counterexample. Find a case where it doesn't work. A consistent formula. A formula is consistent if and only if it has at least one true interpretation in some non-empty domain. If there's some way that the conjunction, I keep saying conjunction because this is usually, formula is usually, when we talk about being consistent, it's usually a conjunction of all our premises. If I can find some interpretation that makes all my premises true, then they're consistent. So I take the conjunction of all my premises, that's now a formula, and that formula, or the conjunction of my premises, is true if I can find some interpretation that makes it true. At least one interpretation, right? So before, once we were dealing with, as our premises, we had x, q, y, or y, q, x for all y, right? And we had x, what was the other one? Oh yeah, transitive, x, q, y, and y, q, z implies x, q, z. Are these consistent? Yes, we came up with an interpretation where both of these were true. And remember, it was for all x, for all y.
Right, you couldn't create a
For all x, for all y. So,
you couldn't create a contradiction within those
x for all y, for all z. So make my formula the conjunction of these two sentences. And is my formula consistent? Yes, because I can find an interpretation where both these things are true. What's an example of one that's not consistent? A contradiction. A and not A. Those are not consistent. There's no interpretation I can find that makes that true. Right? So, 3 major ways that we use interpretations. We use interpretations for proving an argument invalid. That's find interpretation that makes it doesn't work, counterexample. Proving premises consistent. That's exactly what we were talking about here. If the conjunction of all your premises, if there's some interpretation that makes it true, then your premises are consistent. Proving an axiom is independent. We didn't talk about that one, but the way that you can prove an axiom is independent. So say I have axiom 1, axiom 2, axiom 3, and I want to know, is axiom 4 independent? What does it mean for axiom 4 to be independent of these axioms?
Can it come out of that?
It can't come out of it. So how do we do that? We show that the argument, this and this and this implies this, is invalid.
Is invalid.
Invalid is an invalid argument.
Why?
That shows that this is independent of these.
Right.
Because think about it. If I could come up with an argument from A1, A2, and A3 to conclude A4,
Then it's not independent.
then I don't need it as an axiom.
Oh yeah.
I can have it as a theorem.
Right.
Right?
Right. I wondered about that. Like, how did Euclid get down to 10?
Not this way.
I'm sure he didn't, but
Euclid.
sometimes I would wonder, okay, am I done with an axiom right now? And then
I'm. Oh.
So here's another way to write it. How can I show that axiom 4 is independent of 1, 2, and 3?
I got it now.
If this, so A1 and A2 and A3 implies A4 is always false.
Right.
If this is an invalid argument, there's no way for this to be true, then axiom 4 can't be concluded from these axioms, so it's independent of them.
And then you assume that it's true.
Well, then we can add it as an axiom, yeah. So, I have my set of axioms. I have these axioms. I have these 4 axioms. I want to know, are they independent? Do I really need all 4 of those? Maybe not. So I test, can I get this from these 3? Can I get this from these 3? Can I get this from these 3? Can I get that from those 3?
So how, you say that's not the way Euclid did it, how does he narrow down the axioms? Or any mathematician for that matter?
It's amazing what he did, because prior to him, mathematical theorems, it's kind of like, you just know given these premises you can come to this conclusion. You know given these premises you can come to this conclusion. He found that some of those theorems apply theorems and apply theorems, and he worked it back to the 10 that he did. How he did that is just astonishing. There's no reason, like, if you know all these mathematical theorems, there's no reason in your head that you should think, maybe there's only a couple assumptions that all these theorems rely on that it comes back to. It's a huge leap in thinking. And it was for sure not the way that they thought in Plato's day, because that's one of Plato's criticisms of math. Is that
It's not consistent.
it's not that consistent. It's that you're just showing that from the premises you get some conclusion.
Right.
And that's not to say that Plato
And that's not always,
belittled math.
that's not always
That was his number one prereq to going to his school.
yeah, you have to be proficient in geometry. Right?
Let none who know geometry enter. Let none who don't know geometry enter here. Or something to that effect is above it. Or let only those who know geometry enter here.
Mm-hmm.
Something to that effect. Because that's what they thought all math was at their time, geometry. But, well, that's not technically true because they specified the 2 fields, number theory and geometry. So I shouldn't say that. But yeah, so it's not that he belittled it. It's just one of his criticisms of it is that there's not some, he called them first principles that you can derive it all from. Euclid actually did that work. He comes several hundred years after Plato, but absolutely amazing what he did. I mean, there's a reason it's the most published book in history.
Aside from the Bible.
No, more published in the Bible.
Aside from the Bible.
I think it's more published.
Yeah, but it's 2,000 years older.
I don't know how you can
Well, I don't know about that.
Oh, no.
I mean, when did the
But
printing press
it's-
come
it's
out?
not-
The
it's
Bible's
not
been
2,000.
printed way more. Not published more. I think. I could be wrong. Maybe wrong. But the point is it's way out there.
Yes.
And the story goes that it was the first book printed after the Bible. So after
Okay.
Gutenberg came out with the printing press, he did the Bible. After that he did Euclid's Elements. Very basic. Okay, so that's that. You can read more examples.
So is that all of 2?
2 is very long, very wordy, lots of explanation trying to help all these things make intuitive sense to you. And tons of examples. I probably only did like a fourth the examples
I've kind of
in there.
Why do you
That's
make,
what
but it's
I
so
read
simple,
all
why
the
is it so complicated?
definitions. I read all the definitions, but I didn't get to all the examples.
Because it keeps using words that we don't have rigorous definitions for. And so the way he's trying to compensate for that is by giving lots of examples.
So how did you do it?
I did it a similar way. I mean, I used some of the examples that he has, but then I also just talked a lot. Like, we had a lot of conversation about an operation being closed. Now, you already knew what it meant for an operation to be closed, but readers of this book, as a general rule, there's no reason for them to know that. And so that's one of the conversations that he has to have
Isn't
there.
he trying to build this book up from nothing, basically?
You're trying to build a book up from nothing, but understand you're doing 2 things. You're building the theory, but you also need to appeal to the intuition.
Right.
And math is a great field to appeal to your intuition.
Uh-huh.
So we'll use math to appeal to your intuition while building the theory.
Right.
Okay, so that's 4.2. We'll start 4.3 next time.
Oh, we're done with 4.2.
Yeah, this is where it ends. It's just, I'm telling you what I didn't go over was a bunch of examples of seeing all these different things in action.
Okay.
So you're saying, how do you show that formula is consistent? He has tons of examples for that. What does it mean to show that axioms are independent? He has examples for that. So he has examples for all these things that I don't have listed here.
And we're not going to do any.
I just did the examples he had for making sure you understood this,
Right.
because this is the key part. These other things you'll kind of get just as we go, as we're using them, period. But I shall read through his examples if what I said about them doesn't make sense. Good?
Mm-hmm.
So, we'll call it there. And sorry about not getting the other lecture online yet.